Imagine a particle smaller than imagination itself, appearing in the void, a flicker of existence that should not be noticed. Yet, when studied, it whispers something unsettling. Its path does not move forward as all things do, but seems to reverse, as though reality itself were playing backwards. A cosmic riddle is placed before us. In that instant, a riddle that cuts to the deepest assumptions of what it means to live in time. Time, the silent river that carries us from birth to death, from past to future, from memory to expectation, suddenly looks fragile, almost like a trick. If a particle can move against its current, if matter itself can rebel against the flow we take for granted, then everything we know of reality may be incomplete. The screen fills with vast cosmic imagery, galaxies spinning, stars burning, oceans churning with relentless waves, all symbols of time's endless forward march. Yet, hidden within these grand motions, this particle hints that there is another direction, another possibility, something we are not meant to see. The idea of time moving in reverse is not merely strange. It is deeply unsettling. Our lives are built upon time's one-way road. We grow older, we remember yesterday, we plan for tomorrow, and every second lost can never be reclaimed. But imagine for a moment, if 1 second did not follow another in a straight line. Imagine a life where the end precedes the beginning, where the echo is heard before the sound, where the shadow is cast before the light. That is what this particle suggests. In its flickering motion, it dares to ask, what if time is not what we think it is? The mystery grows, and as we stare closer, we are pulled into questions we may not be ready to confront. Science tells us that particles obey laws, that they are the building blocks of reality, each following equations etched into the foundation of the universe. Yet this particle, this anomaly, dares to break those laws, or rather, to reveal a hidden law that we have not yet grasped. Is it moving backward through time, or is it revealing that time itself is not linear, not absolute, but something far stranger? With every frame, with every measured flicker, the mystery deepens. It is as if the universe has left us a secret, a doorway between what we know and what lies beyond. This opening mystery is not simply about physics, it is about the human experience itself. Because to imagine time reversed is to imagine a reality where nothing is permanent, where endings are beginnings, and where cause and effect are rewritten. What would it mean if we could reverse time? Could we undo mistakes, erase tragedies, reclaim what was lost? Or would it bring chaos, unmaking everything we know? The emotional weight of this question lingers, because it is not just science that is at stake, but meaning itself. Visions of history unfold, battles fought, empires rising and collapsing, human lives flashing across centuries, each step a forward march. Now, the film contrasts these images with the single particle moving against the flow, as if mocking the certainty of history itself. The viewer is drawn into a contrast between the inevitability of time and the possibility of breaking free from it. Hope and fear merge, the desire for freedom against the terror of instability. And so, the documentary begins not with an answer, but with a question. One that feels alive, unresolved, urgent. The mystery is set. A particle, perhaps moving backwards in time, perhaps showing us that time is not what we thought. As the scene fades into darkness, the question echoes. What if the arrow of time is only an illusion? What if the universe hides a truth that overturns our deepest assumptions? The stage is set for a journey that will not just explore physics, but shake the very foundation of how we perceive existence itself. Time has always been both familiar and mysterious, a companion in every breath, yet impossible to hold. Humanity's earliest civilizations looked to the sky, watching the shadows of the sun creep across stone, measuring days by the slow dance of light and darkness. Ancient monuments aligned with solstices stand as reminders that, long before modern physics, people were already obsessed with capturing the flow of time. To them, time was circular, repeating endlessly with the seasons. Life, death, harvest, and rebirth formed a cycle that mirrored the cosmos itself. In those ancient minds, time was not an arrow but a wheel. Yet within that wheel lay a deeper yearning, to know why time flows at all, and whether it could ever be escaped. As centuries passed, time became something more structured. Water clocks dripped steadily in temples, sand trickled through hourglasses, and mechanical gears began to tick in towers across medieval cities. These inventions reflected a growing belief that time was regular, steady, a universal heartbeat that could be measured. For farmers, it meant when to sow and reap. For sailors, it determined navigation across oceans. For kings, it ordered calendars of wars and treaties. Time became a force not just of nature, but of power, ruling societies as much as laws and armies. Yet, even as the ticking of clocks gave the illusion of control, mysteries lingered. Was time truly constant, or was it only an invention of the human mind? Then came Newton, who described time as absolute, an invisible stage upon which the universe unfolded. For him, space was a vast arena, and time was its ever-flowing river, moving forward at the same rate everywhere, unaffected by anything. This view dominated for centuries, comforting in its certainty. If the laws of mechanics could describe falling apples and orbiting planets, surely they could describe the passage of moments as well. Time was a reliable backdrop, universal and unquestioned. But comfort has always been fragile in science, and the universe had more unsettling truths to reveal. Einstein shattered this picture with his theories of relativity, transforming time from a rigid stage into a pliable dimension, intertwined with space. Suddenly, time was not absolute but relative, stretching and compressing depending on speed and gravity. Imagine twin brothers. One stays on Earth, the other travels near the speed of light, and upon reunion, the traveler is younger. Imagine clocks near a black hole ticking slower than those far away. These were not dreams, but measurable realities. The comforting certainty of Newton's time dissolved, replaced by a flexible, dynamic concept that bent under the weight of mass and motion. Time was no longer universal but personal. For ordinary human life, these effects are almost invisible, but for the cosmos, they are profound. Stars live and die, galaxies collide, black holes devour light, all under the strange rules of spacetime. Relativity paints a universe where past, present, and future might coexist in a four-dimensional block, with time as a coordinate, like height or width. In this vision, the flow of time may be an illusion, and what we call the present is only the point our consciousness inhabits. It is a revelation both awe-inspiring and deeply unsettling. Yet, even relativity does not fully explain time. The laws of physics, from Newton to Einstein to quantum mechanics, are mostly reversible. Equations can run forward or backward without contradiction. If a billiard ball rolls and strikes another, the mathematics works the same in reverse. And yet, our experience screams otherwise. We remember the past, but not the future. We grow older, never younger. We watch shattered glass scatter across the floor, but never reassemble itself. Somewhere beyond the equations, time has an arrow. The second law of thermodynamics, with its principle of entropy, begins to explain why disorder tends to increase, and with it, the direction of time emerges. Ice melts, heat dissipates, stars burn out. The universe is winding down, and that winding gives us a sense of before and after. Still, the mystery is far from solved. Is entropy the true reason time flows forward, or is it only one layer of a deeper truth? Some physicists argue that entropy does not explain the arrow of time, but merely describes it. Others suggest that the Big Bang set the universe in a low-entropy state, and from that improbable beginning, the arrow was born. The very fact that we can question whether time flows, fundamental or emergent, reveals how incomplete our understanding remains. Philosophers, too, wrestled with this puzzle. To Augustine, time was elusive. The past exists only in memory, the future only in anticipation, and the present vanishes as soon as it is named. To Kant, time was not something outside us, but a structure of the human mind, shaping how we experience reality rather than existing independently. These reflections blur the line between physics and perception, suggesting that time may not be a property of the cosmos at all, but a way the human brain orders events. And yet, the particle we glimpsed at the beginning seems to disagree. Its motion suggests that time is not fixed, not simply human imagination, but a dynamic part of physical reality that can be bent, challenged, or even reversed. If time were purely mental, how could particles rebel against it? This tension between experience and experiment sharpens the mystery. The section closes with a cinematic contrast: ancient sundials casting shadows, medieval clocks striking, Einstein's equations dancing across chalkboards, all dissolving into the strange flicker of the particle moving backwards. Across cultures, centuries, and theories, humanity has tried to capture time, to explain it, to command it. And yet it slips away, more mysterious than ever. The audience is left with the lingering question: if time is not absolute, if it is not universal, if it may not even flow as we think, then what truly governs the unfolding of existence? The deeper we peer into the fabric of reality, the stranger it becomes. What once seemed solid, indivisible, and permanent has been revealed as a teeming realm of particles, each more mysterious than the last. At first, humanity believed atoms were the smallest units of matter, unbreakable and eternal. But when the atom was split, a hidden kingdom was discovered, a zoo of bizarre entities darting in and out of existence, a restless menagerie where the rules of common sense no longer apply. Here, in this quantum world, particles flicker, vanish, and reappear, behaving less like objects and more like fleeting whispers of possibility. It is a realm both magnificent and terrifying, because in its chaos lies the foundation of everything we are. Picture the proton, massive compared to its companions, made of quarks bound tightly by gluons in a dance so violent and ceaseless that it resembles a storm held together by invisible forces. Imagine the electron, a ghostly traveler orbiting in clouds rather than neat paths, existing in many places at once until measured. Then there is the neutrino, nearly massless, able to slip through the densest matter as if it were smoke. Alongside these come particles that almost seem invented by imagination: muons, taus, strange quarks, charm quarks, bosons, mesons, the list stretching further with every discovery. Each one is a character in the vast story of the universe, essential yet elusive, real yet fleeting. Cinematic imagery unfolds across the screen. A beam of light splits into shimmering motes, each mote transforming into a new creature, some bright and stable, others wild and short-lived, decaying in fractions of a second. A voice explains that the world we know, air, water, stone, flesh, rests on this chaotic underworld. Particles emerge in colliders like fireflies in the dark, their tracks curling and scattering in ways that hint at a hidden order, a secret logic. Yet the logic is not the logic of human intuition. These particles do not obey the simple cause and effect of the macroscopic world. Instead, they seem to follow probabilities, as though the universe itself hesitates before choosing what will exist. The term particle zoo was once spoken half in jest by physicists overwhelmed by the sheer number of discoveries in the 20th century. Detectors revealed an explosion of new particles, many with lifespans so brief they barely exist, yet each one demanded a place in the catalog of reality. This zoo is not tidy, not a neat arrangement of cages, but a wild and sprawling cosmos within a cosmos. The screen fills with swirling animations of particles colliding and decaying, their trails marked in luminous arcs as if the very canvas of existence is alive with sparks. The viewer is left with the sense that the universe hides a labyrinth beneath its surface, a living jungle of invisible actors. But chaos is only one side of the story. Out of this zoo, patterns emerge. Physicists found that particles could be grouped, families forming out of the apparent disorder, governed by deep symmetries. The standard model of physics arose like a map of this strange territory, assigning quarks, leptons, and bosons to their roles, each one vital to the structure of the cosmos. Quarks combine to form protons and neutrons, the building blocks of matter. Leptons, like electrons and neutrinos, dance around them, forming atoms. Bosons act as messengers, carrying the fundamental forces, the photon for light, the gluon for the strong force, the W and Z bosons for the weak force, and the Higgs boson, granting mass itself. The zoo, once bewildering, became a chart, a table of existence, a framework through which the invisible could be understood. And yet, even within this framework, mystery dominates. The standard model explains much, but not all. Why are there exactly 6 kinds of quarks? Why 3 generations of leptons? Why does matter vastly outweigh antimatter in the observable universe? Each unanswered question is like a shadow in the zoo, a creature half seen, a hint that something larger remains hidden. The sense of wonder deepens into unease. If the zoo we know already defies common logic, what lies beyond it? What new particles are waiting to be discovered? What new rules might they obey? The narration slows, focusing on a single concept, antiparticles. For every particle in this zoo, there exists a mirror version, identical in mass but opposite in charge. Electron has positron, proton has antiproton. When particle meets antiparticle, they annihilate in a burst of pure energy, disappearing as quickly as they came. It is an eerie symmetry, one that feels both elegant and dangerous. Cinematic images show pairs of particles colliding, erupting into flashes of light like cosmic fireworks, hidden in the quantum sea. The zoo is no ordinary collection. It is a hall of mirrors, filled with doubles and shadows, each reflecting a truth about the nature of existence. This is where the story of the backward-moving particle begins to sharpen. For in the world of particles, time does not behave as it does for us. The equations describing these tiny entities often allow for 2 directions of motion, forward and backward. For most, we only observe the forward path, in harmony with the flow of entropy. But certain interpretations, certain strange readings of experiments, suggest that at least some of these creatures may slip the leash. They may reverse their path, not only in space but in time itself. What to us looks like a particle could, in another perspective, be an antiparticle moving backwards in time. The zoo suddenly becomes not just a collection of strange creatures, but a theater where the rules of past and future may be rewritten. The section closes with a sweeping montage, ancient diagrams of atoms dissolving into the tracks of colliders, electrons orbiting like ghosts, neutrinos streaking invisibly through the earth, annihilations flashing like lightning in the dark. The narration lingers on the thought that this zoo is more than curiosity. It is a key to unlocking what time truly is, and perhaps a doorway into the unsettling possibility that time itself is not fixed, not one way but malleable. Within this zoo, hidden in its chaos and symmetry, the mystery of the backward-moving particle waits to be uncovered. In the mid-20th century, at a time when the quantum zoo was overwhelming even the sharpest minds, two physicists dared to ask a question that seemed almost unthinkable. What if antimatter is not merely matter's opposite, but matter itself moving backwards in time? Richard Feynman, the playful genius known for turning physics into diagrams, and Ernst Stueckelberg, a quieter but equally visionary thinker, both arrived at this radical interpretation. Their idea was not born out of fantasy, but out of mathematics, equations that seem to whisper that time might not be as rigid as we believe. To most, antimatter was already strange enough. But to suggest it might actually be time-reversed matter was to throw open a door that led not only deeper into physics, but into philosophy itself. Imagine a particle traveling forward, its motion predictable, its energy aligned with the arrow of time. Now imagine flipping the sign, allowing the same equations to describe a particle retracing its steps, moving backwards into what we call the past. Feynman and Stueckelberg realized that these two views were not separate. What one person calls a particle moving forward could equally be described as an antiparticle moving backward. The distinction was not in the mathematics, but in perspective. Suddenly, antimatter became more than a curiosity. It became a hint that the very flow of time might depend on how we choose to look at it. The cinematic narration draws the viewer into Feynman's notebooks, sketches of swirling diagrams that turned complex equations into visual maps. His Feynman diagrams showed particles colliding, exchanging photons, disappearing and reappearing, arrows drawn not only in space, but in time. In those arrows, he embedded the bold interpretation. Antiparticles were simply ordinary particles whose time arrows pointed the other way. With a stroke of chalk, the boundary between forward and backward blurred. The zoo of particles gained a hidden symmetry, a reflection across time itself. To grasp the weight of this, the documentary invites the viewer into a thought experiment. Picture a film of two particles colliding. Run it forward, and you see matter and antimatter annihilating in a burst of energy. Run it backward, and you see energy crystallize into a pair of opposites. To the laws of physics, both versions are valid. The equations make no judgment about which direction is real. To nature, forward and backward may be two faces of the same truth. What we call antimatter may be no more than matter caught in reverse. This idea unsettled many. Physics was already straining under the weight of quantum paradoxes, and to add time reversal into the mix threatened to fracture intuition even further. But Feynman, with his characteristic confidence, embraced the strangeness. He joked that an electron traveling backward in time looked to us like a positron, the electron's antimatter twin. Stueckelberg had proposed the same idea years earlier, though his version remained less known. Together, their vision formed one of the most haunting interpretations in science, that the universe does not distinguish between past and future as sharply as we do. Cinematic visuals show two beams of particles racing toward each other, then freeze in slow motion. As the narration continues, one beam reverses the frames, rolling backward, while the other continues forward until they meet in perfect symmetry. The image embodies the heart of the Feynman-Stueckelberg idea. Time is not absolute, and antimatter is not alien. It is us, seen from the other side of the temporal mirror. The implications extend far beyond physics. If antimatter is matter reversed in time, then the universe may contain more than one arrow of existence. Could there be entire domains of reality flowing opposite to ours, invisible yet adjacent? Could every annihilation we observe be a fleeting handshake between forward-flowing and backward-flowing worlds? The interpretation does not answer these questions, but it dares us to ask them. It replaces certainty with wonder, and in doing so unsettles our deepest assumptions about causality and order. And yet, as radical as it was, the interpretation did not break physics. It fit neatly into the equations, making predictions consistent with experiment. The universe seemed to permit this reversal, as if leaving a trail of breadcrumbs toward a truth we have not yet fully grasped. For many physicists, it was easier to treat the idea as a mathematical trick, a useful convenience without deeper meaning. But for those willing to look beyond utility, the thought lingered. What if the trick was reality itself? What if the mathematics was showing us not only how particles move, but how time itself is woven? The narration slows, reflecting on Feynman's legacy, his diagrams etched into the memory of physics, his daring interpretations challenging the boundaries of imagination. Stuckelberg, less celebrated but no less bold, fades into history with quieter recognition. Together, their vision stands as a milestone, a place where science touched philosophy, where an abstract idea carried emotional weight. For if time can be reversed at the most fundamental level, what does that mean for human experience, for memory, for fate? The section ends with a dramatic pause. The camera zooms in on the flickering particle once more, the one introduced at the beginning of the documentary. Its trajectory bends strangely, a line on a graph that curves backward. To some, it is a neutrino. To others, a mathematical artifact. But through the lens of the Feynman-Stuckelberg interpretation, it may be something more profound. A glimpse into time's secret flexibility, a tiny messenger whispering that the universe is far stranger than we dare to believe. The viewer is left with the haunting question. If antimatter is matter moving backward in time, then is the particle we see today not just unusual, but proof that reality itself runs in two directions? They are called the ghost particles, and for good reason. Every second, trillions of them pass through your body, streaming from the sun, from distant stars, from nuclear reactions on Earth, and you never feel a thing. They slip through walls, oceans, and planets as if matter were made of smoke. To detect even a fraction of them requires building vast machines, buried deep underground, filled with pure water or liquid argon, waiting for a rare spark of interaction. Neutrinos are almost nothing, and yet they are everywhere. Invisible, untouchable, indifferent to our existence, they form one of the most enigmatic presences in the cosmos. If any particle could carry the secret of time reversal, it is the neutrino. Discovered in the mid-20th century, neutrinos were first proposed to solve a problem. In nuclear decay, something seemed to be missing. Energy vanished, momentum did not balance, as if nature had lost its accounting. To save the laws of physics, Wolfgang Pauli suggested an unseen particle carried away the missing quantities. He apologized for what he called a desperate solution, doubting such a ghostly entity could ever be observed. Yet, in time, the neutrino was confirmed, its presence inferred in faint flashes of light deep in detectors shielded from noise. What began as a theoretical fix became one of the most profound discoveries of the century. The cinematic narration brings the audience into cavernous chambers carved into rock, where detectors the size of cathedrals stand in silent darkness. Vast tanks of water or ice are lined with sensitive instruments, each waiting for the briefest flash of Cherenkov radiation, a cone of blue light emitted when a neutrino finally collides with an atom. These fleeting sparks are the footprints of the ghost. Without them, we would never know neutrinos exist. The imagery contrasts the immensity of the detectors with the minuteness of the particle, capturing the strangeness of a universe where the smallest things require the largest machines to glimpse. Neutrinos are not just elusive, they are strange in their very nature. Unlike other particles, they come in three flavors: electron neutrino, muon neutrino, and tau neutrino. But these flavors are not fixed. As neutrinos travel, they oscillate, morphing from one type to another in flight. This is not supposed to happen according to the simplest versions of the Standard Model. To oscillate, neutrinos must have mass, however tiny, and for decades they were assumed to be massless. Their shifting identities shattered that assumption, forcing physicists to rethink how particles acquire mass and how the universe itself evolved. The strangeness does not stop there. Neutrinos and their antiparticles, antineutrinos, raise one of the deepest questions in physics. Are they truly distinct, or are they the same entity traveling in opposite directions of time? This possibility, known as the Majorana hypothesis, suggests that neutrinos could be their own antiparticles. If proven true, it would blur the line between matter and antimatter, hinting that the neutrino embodies both. And if the neutrino is both, then the idea of moving backward in time ceases to be abstract and becomes a tangible feature of the particle itself. Cinematic imagery fills the screen with solar neutrinos streaming from the heart of the sun, products of nuclear fusion, pouring across space in endless numbers. Others emerge from supernovae, carrying with them the last screams of dying stars. Some are born in reactors on Earth, whispering secrets of the atomic nucleus. They are everywhere, traveling close to the speed of light, unimpeded by barriers, unbound by ordinary rules. The narration lingers on the haunting realization: we live in a universe flooded by invisible rivers of neutrinos, and only recently have we begun to notice them. What secrets might they carry? The mystery deepens with the discovery of anomalies. Some experiments show that neutrinos do not behave exactly as predicted. In certain cases, the number of detected neutrinos does not match the expected amount, as though they are disappearing into hidden dimensions or morphing into undiscovered types. These discrepancies fuel speculation about sterile neutrinos, hypothetical particles even more ghostly than the known ones, interacting only through gravity and perhaps carrying within them a clue to time itself. If sterile neutrinos exist, they might link ordinary matter to dark matter, the unseen mass shaping galaxies. In them could lie the bridge between what is visible and what is hidden, between the forward flow of time and its reversal. The narration slows, reflecting on the haunting elegance of the neutrino's role in the cosmos. Without neutrinos, stars could not burn in the way they do. Without neutrinos, the universe might not have developed its structure. And yet, for all their abundance, they remain almost entirely undetectable. It is as if the universe has placed its greatest secrets in plain sight but made them nearly impossible to grasp. The audience feels both awe and frustration, drawn into the paradox of a particle that is everywhere but untouchable, vital but unknowable. To scientists, neutrinos are not only a curiosity but a potential key to some of the biggest puzzles. Why is there more matter than antimatter in the universe? If matter and antimatter were created in equal amounts during the Big Bang, they should have annihilated each other, leaving only radiation. And yet, matter remains, forming stars, planets, and people. Somewhere in those first moments, a subtle imbalance tipped the scales. Neutrinos may hold the answer. If their behavior breaks the symmetry of matter and antimatter, they could explain why the universe exists at all. In this way, the neutrino is not just a ghost but a creator, a particle that decided the fate of everything. Cinematic tension builds as the narration shifts to experiments like Dune, the Deep Underground Neutrino Experiment, and Japan's Super Cameo Candy, monumental efforts to capture the truth of these elusive entities. Buried beneath mountains and plains, scientists wait for whispers from the cosmos, measuring with patience that stretches across decades. They are not only looking for oscillations or sterile states but for signs that neutrinos might betray the arrow of time. Could their transitions reveal backward causality? Could their very existence show that time, like neutrino flavor, can change its identity? The section closes with a haunting contrast. On one side, the immensity of the universe, glowing with stars, supernovae, and black holes. On the other, the smallest flicker of light in an underground detector, a single neutrino finally noticed after passing through light-years of matter. The narration lingers. Perhaps in these ghosts lies the greatest secret of all, the secret of time's true nature. If neutrinos can be both matter and antimatter, if they can vanish and reappear, if they can oscillate across identities, then perhaps they can also cross the boundary of past and future. The enigma of the neutrino becomes not only a puzzle of physics but a doorway to the possibility that time itself is not as one-directional as it seems. For decades, neutrinos were expected to behave in ways that matched the clean predictions of the Standard Model. They were ghosts, yes, but ghosts that followed rules, streaming endlessly yet without surprises. But as experiments grew larger and more precise, something began to emerge, a series of anomalies, cracks in the framework, whispers that the universe was not obeying its own script. These discoveries were not loud, not explosive, like a new planet in the sky, but subtle, quiet, almost fragile. And yet their meaning was enough to shake the very foundations of physics. It began with the solar neutrino problem. Detectors buried underground in the late 20th century recorded fewer neutrinos from the sun than theory predicted. The sun was burning, fusing hydrogen into helium, releasing an expected torrent of ghostly particles. But only a fraction arrived. For years, physicists wondered if they had miscalculated the fusion reactions, if something was wrong in the heart of the sun itself. But the sun was not at fault. Instead, the mystery hinted at something much deeper. Neutrinos were changing identity in flight, oscillating between flavors, slipping beyond the expectations of the Standard Model. The moment this truth was confirmed, physics itself trembled. Neutrino oscillations meant neutrinos had mass, however slight, and the Standard Model had insisted otherwise. The most successful theory of particle physics, tested countless times, was incomplete. The equations that mapped the zoo of particles, the framework that had explained the building blocks of reality, suddenly showed a flaw. Something fundamental had been overlooked, and in that gap lay the possibility of a deeper reality. The cinematic narration describes this revelation with rising tension, accompanied by imagery of stars trembling, detectors sparking with faint flashes of light, and equations shattering into fragments. But neutrino oscillations were not the only anomaly. Other experiments began reporting results that suggested neutrinos were vanishing into forms we could not see, perhaps into sterile neutrinos or into states that defied known physics. Some measurements hinted at signals appearing before they should have, data points that seemed to flirt with the forbidden idea of faster-than-light travel. These results were often controversial, their validity challenged, their interpretations debated. Yet even the suggestion that particles could slip outside of causality sent shivers through the scientific world. The question echoed, are we glimpsing not just new particles, but new laws of time itself? Cinematic imagery builds around this tension. Vast colliders hurl beams of particles at near-light speeds, while underground chambers wait patiently in the dark. The narration emphasizes the drama not of certainty, but of doubt. Science thrives on anomalies, because anomalies are the cracks where truth hides. When experiments refuse to match predictions, it means the universe is speaking in a language we have not yet learned. And in those mismatches, Some physicists see the faint outline of time's reversal, the suggestion that particles may not always march forward as we do. For the scientific community, these discoveries provoked both exhilaration and fear. On one hand, anomalies open the door to revolutions. On the other, they threaten the structures carefully built over decades. The Standard Model had been the crown jewel of physics, explaining everything from electromagnetic waves to nuclear forces. To suggest it was incomplete felt like heresy. But the neutrino, the ghost particle, had no loyalty to human frameworks. It whispered that reality was bigger, stranger, and less predictable than our neat charts allowed. The narration pauses on the emotional weight of this revelation. Imagine devoting years to building a framework that explains the cosmos, only to find that a particle you can barely detect has broken it. Imagine standing in a dark laboratory, waiting for a single flash of light, and realizing that flash means our understanding of time, mass, and matter must be rewritten. That is the scale of the discovery that shook physics. It was not the loud crash of contradiction, but the soft whisper of an unseen particle refusing to behave. As the section nears its end, the viewer is reminded that anomalies are not answers, but invitations. The mysteries of neutrino behavior do not yet prove time reversal, but they create a space where such radical ideas can breathe. They unsettle certainty, making room for imagination. The camera lingers once more on the faint glow of a neutrino interaction in a dark detector, the smallest of sparks in the vast silence. The narration closes with a question, heavy with suspense. If neutrinos can bend the rules we thought were absolute, what other secrets of time might they be hiding? When Richard Feynman introduced his diagrams, he did not simply give physicists a new way of writing equations. He gave them a new way of seeing. Complex interactions between particles, once buried inside impenetrable mathematical symbols, became pictures, arrows, lines, loops, sketches of reality's most fundamental conversations. A photon meeting an electron, two protons colliding, a neutrino slipping silently away, all of these could be drawn, and in those drawings was a strange elegance. But hidden within that elegance was also a subtle invitation to think differently about time. Because in Feynman's language, the direction of an arrow was not fixed. The mathematics allowed a particle to be drawn as if it were moving backward in time. This idea was not just a curiosity, not simply an abstract flourish. In his equations, antiparticles could be interpreted in exactly this way. To some physicists, the antimatter counterpart of a particle was not a different object at all, but the same particle traveling against the current of time. In the world of equations and diagrams, where time does not flow as it does in human experience, this was a consistent and even natural way to think. But in the world of human perception, it was unthinkable. What would it mean if the antimatter electron, the positron, was not another species of matter, but the electron itself moving backward across time's arrow? The narration lingers here, showing Feynman's bold sketches, his chalk lines on a blackboard. Each arrow on the page represents not only a path through space, but through time itself. The forward arrow we recognize, the backward arrow we resist. Yet the equations treat them with equal weight, equal reality. To mathematics, the difference is only a sign, a reversal, a change in perspective. But to the human mind, it is a challenge to meaning itself. Feynman's genius was not only in solving problems, but in making the incomprehensible visible. His diagrams revealed that what we call causality, a happening before be, was not a sacred law, but a convention written into our perception. In the quantum world, events could be described as if they unfolded forward or backward. The mathematics did not protest. Instead, it showed that both descriptions were possible, and sometimes equally valid. Consider the simple act of two particles meeting. One interpretation shows them colliding, exchanging energy, and moving apart. Another interpretation shows one particle moving backward in time, annihilating with another, the same interaction seen from a different angle of temporal description. Both stories, though radically different in their narrative, describe the same underlying reality. It is not that the universe has changed, but that our interpretation of time's role in the story has shifted. The cinematic imagery swells as the narration unfolds. Chalkboard diagrams dissolve into swirling galaxies, arrows of light cutting across the darkness of space. The visuals suggest that perhaps the universe itself is a grand diagram, each star and each particle a line in some hidden sketch. But the most unsettling implication remains. If mathematics allows for backward time, why do we not see it in our lives? Why is our experience so stubbornly one-directional when the equations refuse to be so limited? Feynman himself was playful, almost mischievous, in the way he treated these paradoxes. For him, the strange idea that antimatter was matter moving backward in time was not a frightening contradiction, but a delightful insight into how flexible reality could be when seen through the lens of mathematics. He described it casually, almost with a shrug, as though suggesting that our deepest assumptions about time were only habits of thought. The narration emphasizes this contrast, the brilliance of a mind unafraid of paradox against the backdrop of a universe that might be stranger than anyone dared to imagine. The strangeness deepens when we realize how naturally the mathematics accommodates reversal. In classical life, time reversal is absurd. A shattered glass cannot leap back into wholeness. Smoke cannot flow back into a flame. But in quantum equations, time symmetry is almost built in. Reverse the signs, flip the arrow, and the math still works. The difference is not in the laws themselves, but in the boundary conditions, the way we set up the story. The equations whisper, time is not the universe's law, but ours. The narration brings us to a crucial emotional point. Imagine reality as a film. In our lives, the reel plays forward, and every frame builds on the next. But mathematics does not care whether the reel plays forward or backward. The equations remain true either way. The image of a reel running in reverse plays on the screen. Cities reconstructing, stars uncollapsing, people growing younger. The viewer feels both wonder and unease. If physics allows for such reversals, why are we locked into only one direction? What force binds us to the forward march when the equations permit both? The section continues by highlighting the philosophical weight of this idea. Feynman's diagrams are not simply tools, they are mirrors held up to our assumptions. They force us to ask whether the arrow of time is a fundamental feature of the universe or an emergent illusion, a byproduct of deeper rules. Perhaps time's arrow is not absolute, but contingent, a shadow cast by entropy, by probability, by the way complexity builds. If so, then Feynman's backward arrows are not fantasy, but glimpses of another way reality might unfold. The camera lingers on the face of Feynman himself in archival footage, his voice filled with humor as he describes how he sees the universe. He laughs at paradox, he embraces the absurd, because to him the absurd is where truth often hides. The narration ties this spirit back to the theme of the film, the possibility that particles could move against time's arrow, not as science fiction, but as legitimate interpretations born of mathematics. And so, the strange mathematics of Feynman leaves us with a challenge. If the simplest diagrams of particle physics permit time to flow in both directions, then perhaps time is not the solid wall we imagine, but a curtain, thin and permeable, hiding dimensions of reality we have yet to see. The section closes on this haunting question. If the equations do not forbid backward time, who are we to insist it cannot exist? The viewer is left with wonder and disquiet, standing on the edge of a mystery that mathematics reveals, but does not resolve. When scientists first discovered antimatter, it seemed like a mirror-world reflection of everything familiar. For every particle of matter, there was an opposite, identical in mass but opposite in charge. The electron had its mirror twin, the positron. Protons had antiprotons. Neutrons, too, carried opposites. At first glance, this symmetry suggested balance, like two sides of a cosmic coin. Yet, hidden in this balance was something more unsettling. Antimatter could be thought of as matter moving backward in time. It was not only an opposite, it was a reversal, a shadow that carried the signature of a temporal inversion. The narration begins with vivid imagery. A human face reflected in a mirror, perfectly familiar but also disturbingly reversed. The left is now right, the right now left. Antimatter, too, seems to be this reflection, an eerie double. When a particle of matter meets its antimatter counterpart, they do not coexist. They annihilate, vanishing into pure energy, into photons. This annihilation is a kind of cosmic punctuation mark, a violent erasure. But, through the lens of Feynman's interpretation, this annihilation could be reimagined as a single particle's timeline looping back on itself, one moment moving forward, the next reversed. What looks like destruction could also be a different form of continuity. In the laboratory, antimatter is not fiction. We have trapped it, measured it, watched its behavior. In PET scans used in hospitals, positrons are harnessed to create images of the living body. In high-energy collisions inside particle accelerators, antimatter particles flash into existence, stay for fractions of a second, and then vanish in annihilation. To the equations of physics, this is no mystery. But to the human imagination, antimatter is haunting. Why does it exist at all? Why is it so perfectly symmetrical to matter, yet so elusive in the natural world? Cinematically, the narration contrasts the microscopic with the cosmic. On one level, positrons appear in medical imaging machines, giving us glimpses inside living tissue. On another, antimatter seems to represent a deeper principle of the universe, a law that insists on symmetry, balance, and the possibility of reversal. The viewer is pulled into this dual perspective, intimate and vast, comforting and terrifying. The story then moves into the great cosmic mystery. If matter and antimatter were created in equal amounts during the Big Bang, why is the universe made almost entirely of matter? Where did the antimatter go? Did it annihilate itself in those first moments, leaving only a tiny imbalance in favor of matter? Or is there a region of the cosmos hidden from us, where antimatter reigns, galaxies made of inverted matter, orbiting distant stars we cannot yet see? The camera sweeps across deep space, galaxies spinning like mirrored reflections. The narration poses the question: if we could travel there, would we recognize it, or would it seem like stepping into a reversed universe, one where the flow of time itself might feel different? The philosophical weight of antimatter grows heavier when framed as time reversal. If a positron is an electron moving backward in time, then annihilation is not destruction but an intersection, the crossing of two timelines. The particle and its antiparticle are not separate things, but two directions of the same being. In this view, the annihilation event is less like an erasure and more like the closing of a loop, a reunion that cancels the journey by folding it back on itself. The mathematics does not demand we think this way, but it permits us to. And once permitted, the imagination is free to wander into unsettling territory. Consider the human experience of time, relentless, forward, irreversible. We cannot step into yesterday. We cannot undo our choices. We cannot meet our own reflection moving toward us from the future. Yet, in the world of antimatter, something like this seems allowed. A positron may be nothing more than an electron retracing its steps, arriving from what we would call the future, departing into what we call the past. If true, this means that every collision in a particle accelerator is not just a clash of matter, but a potential meeting across the boundaries of time itself. The narration tightens around this mystery. Visuals of particles colliding are shown in slow motion, bright flashes of annihilation painted across the screen. Then, as though reversing a reel of film, the explosions pull back together, particles reforming, timelines retracing. The question lingers: are we watching destruction or a hidden continuity? The emotional hook deepens when we reflect on why the universe did not choose symmetry. If matter and antimatter were created in equal measure, why does only matter remain? Was it chance, a small imbalance magnified across billions of years? Or does it reveal a deeper truth, that time itself has a preferred direction, a bias that broke the symmetry, ensuring that one arrow, forward, would dominate the universe we inhabit? The mystery is framed not as abstract physics, but as an existential question. Without that imbalance, without the vanishing of antimatter, we would not exist. We live because time, in some hidden way, broke its own symmetry. The narration invites the audience to imagine an alternative. Suppose the universe had remained perfectly balanced, equal parts matter and antimatter. In that universe, the annihilation would be total, and nothing like us would exist. No stars, no galaxies, no consciousness to ask these questions. In a strange sense, our very existence is built upon the absence of antimatter, upon the shadow of what might have been. And yet, in the mathematics, antimatter is never gone. It remains possible. It remains a partner to every particle, a constant reminder that our universe is incomplete without its reflection. The camera pulls back once more, leaving the viewer with a haunting vision. On one side, our world of matter, familiar and solid. On the other, the ghostly presence of antimatter, like a mirror waiting to be recognized. Between them lies annihilation, but also the possibility of seeing time itself as flexible, reversible, and strange. The section closes by asking the question: if antimatter is matter reversed, then what does that make us? Are we simply one side of a greater whole, blind to the reflection moving in the opposite direction, unseen yet essential? Time for us is a river with a single direction. It carries us forward relentlessly, from birth to death, from the past to the future. Every tick of the clock reinforces this certainty. A glass shatters, and the shards cannot leap back together. Smoke rises, but it does not fall into the fireplace to reassemble the log. Our lives too follow this direction, and we rarely question it. Yet physics whispers something more unsettling. At the deepest levels of the equations, time has no preferred direction. The mathematics describing the smallest particles work just as well forward as backward. To the laws of physics, there is no difference. The arrow of time, the one we feel so deeply, is not written into the rules. It is something that emerges, something that must be explained. The narration begins with the imagery of a desert river, flowing endlessly forward, carving through stone, leaving behind traces of its journey. The voice points out that the river could, in principle, flow the other way. Nothing in the laws of fluid motion forbids it. But it does not. Just as with time, the one-way journey is what we observe, not what is demanded. The contrast becomes sharp, the certainty of our experience against the ambiguity of physics. This mystery forms the heart of the cosmic arrow of time. One explanation often offered is entropy. Entropy is the measure of disorder, the tendency for systems to evolve from order to chaos. An egg cracks, but the pieces do not leap into wholeness again. Entropy grows, and this growth gives direction to time. Yet even this explanation is haunting. Why did the universe begin in such a low entropy state, such an unlikely state of order, so that time could begin its journey toward greater disorder? Why was the universe's beginning so improbably arranged, setting in motion the cosmic arrow that defines everything we know? The narration slows here, letting the weight of the question sink in. It is not enough to say entropy gives us direction. We must ask why the starting line was drawn in such an extraordinary way. The cinematic visuals shift to the early universe, a nearly featureless sea of energy, smooth and uniform, and yet hiding the seeds of time's unfolding. The narration suggests that in those first moments, the arrow of time was born. Every galaxy that formed, every star that ignited, every life that emerged, all flowed from that initial imbalance. Without it, there would be no history, no story, no forward movement at all. And here is where the unsettling possibility enters. If antimatter can be interpreted as matter moving backward in time, then perhaps our arrow of time is not the only one. Perhaps, in some hidden sector of the universe, there exists another arrow flowing in the opposite direction. To us, their existence would look reversed. To them, perhaps we would appear reversed. Both would feel their own arrow as natural, inevitable. Both would see the other as impossible. Yet in the mathematics, both are allowed. The narration paints a haunting image: two universes, born from the same origin, diverging in opposite temporal directions, each one expanding, each one aging, each one feeling its own arrow. From our perspective, theirs would seem to run backward. From theirs, we would be the reversal. The cosmic arrow, then, may not be absolute. It may be a matter of perspective, a property that emerges only within a given frame of reference. The emotional pull grows stronger when the narration connects this to human experience. We are creatures of memory, of anticipation, of stories. Our minds are built to record the past and imagine the future. If the arrow of time were reversed, what would that mean for memory? Would we remember what, to us, lies ahead? Would our stories run in reverse, ending before they begin? The audience is invited to imagine a life played backward, not as a gimmick, but as a genuine existence in a reversed arrow. Would love, loss, growth, and decay hold meaning in such a world, or would meaning itself dissolve without our familiar progression? Cinematic imagery deepens this reflection. A candle burning, the wax dripping downward. The film reel reverses. The wax climbs back into the candle. The flame regrows into the wick. The narration does not dismiss this as absurd, but instead lingers on the possibility that somewhere, somehow, this reversal is real, that another arrow is as legitimate as ours. The mystery is no longer abstract physics. It is the unsettling suggestion that our lived sense of time is not universal. At this point, the narration reintroduces entropy. If our arrow is defined by increasing disorder, then the opposite arrow would be defined by increasing order. In that universe, the shards of glass would leap together, the smoke would fall into the fireplace, the candle would rebuild itself. To us, this seems absurd. But to those within that universe, it would be as natural as our forward arrow is to us. They would call our world impossible. The contrast becomes a mirror. Our sense of inevitability is only a perspective, not an absolute truth. The question then rises, is there any evidence that another arrow exists? The narration acknowledges the silence of physics here. We have no direct proof, only equations that do not forbid it. Yet silence itself can be suggestive. Just as we once believed Earth was the center of the cosmos, only to learn it was one perspective among many, so too might our arrow of time be one among many possible flows. The haunting possibility lingers. We are not special, not unique, even in our experience of time. The section begins to close with a cinematic sweep outward. Stars burn, galaxies rotate, The universe expands, entropy climbs. Time's arrow carries everything forward, unrelenting. And yet, hidden in the mathematics, is the whisper of another arrow, just as real, just as relentless, carrying some other world in the opposite direction. The narration leaves the audience with a lingering question. Is the arrow of time a universal truth, or simply the lens through which we, trapped in one direction, perceive reality? The closing line frames the tension sharply. If antimatter can be seen as matter moving backward in time, then perhaps the universe itself carries within it two arrows, diverging from the same origin, forever unseen by each other. Our arrow feels inevitable, but inevitability is only an illusion born of perspective. The mystery of the cosmic arrow is not why time moves forward, but why it moves at all, and whether somewhere, in the hidden symmetry of creation, it also moves the other way. When most people hear the word antimatter, they imagine science fiction, a mysterious, glowing substance capable of powering starships or destroying worlds. But antimatter is not fiction. It is as real as the air we breathe. It is the twin of matter, identical in every measurable way, except for charge. The electron has a partner, the positron. The proton has its opposite, the antiproton. The neutron, too, has an antimatter counterpart, bound by the same laws but reversed in charge. The universe, at its most fundamental level, seems to keep ledgers in pairs, matter and antimatter, mirrored across an unseen divide. Yet this mirror is not perfect, not equal, and that imperfection holds the key to both existence and to one of the deepest mysteries of time itself. The narration begins with imagery. Imagine standing before a perfect mirror. Every movement you make, the reflection follows. Raise your right hand, and the mirror raises its left. Your reflection seems identical, but it is reversed, subtly wrong, an inversion that feels uncanny if you study it too long. Antimatter is like that. To the laws of physics, it is the mirror of matter. But unlike a simple mirror reflection, antimatter is not trapped behind glass. It exists. It moves. It collides with matter, and when it does, both are annihilated in a burst of pure energy. It is the ultimate undoing, the final handshake where opposites cancel out into light. This act of annihilation is not destructive in the usual sense. It is elegant. Nothing is wasted. The matter and antimatter dissolve into photons, into pure energy that rushes outward at the speed of light. The narration slows here, drawing the audience into the awe of it. Two solid particles colliding, their entire mass converted into energy. It is the most efficient reaction known to physics, far surpassing nuclear fission or fusion. A gram of antimatter meeting a gram of matter would release an explosion greater than a nuclear bomb. And yet, the universe, vast and ancient, contains so little of it that we struggle to catch even fleeting glimpses. Here is where the mystery deepens. According to the laws of physics, the Big Bang should have created matter and antimatter in equal amounts, perfect pairs. For every particle of matter, a twin of antimatter. If that were true, they should have annihilated each other almost instantly, leaving behind a universe filled only with light. No galaxies, no stars, no planets, no us. And yet here we are, surrounded by matter. Something tipped the scales. Somehow, a tiny imbalance occurred. Just enough extra matter survived to form the universe we know. This imbalance, this asymmetry, is one of the great unsolved puzzles of physics. Why is there something rather than nothing? Why did matter win? The narration takes on a tone of suspense. What if the explanation lies not in a simple imbalance, but in the nature of antimatter itself? What if antimatter is more than just matter's opposite charge? What if it is matter, but moving in the opposite direction of time? This interpretation, hinted at by the mathematics of quantum theory, reframes antimatter not as a twin, but as a traveler. To us, a positron looks like a particle moving forward. But some physicists suggest it is more accurate to say it is an electron moving backward in time, slipping along a different path through the dimension we cannot reverse. The cinematic imagery builds. Imagine a mirror, but not one that reflects space. It reflects time. Look into it, and your reflection does not only raise the opposite hand. It walks backward as you walk forward. Antimatter may be such a reflection, the living evidence that time can, in principle, flow both ways. This is not fantasy. It is woven into the equations of quantum electrodynamics, where a particle traveling backward in time appears to us as its antiparticle. The mathematics makes no distinction. Both interpretations are equally valid. But one challenges our most fundamental assumption, that time has only one direction. The narration turns inward now, inviting the audience to imagine, if antimatter is time-reversed, what does that mean for our universe? When a particle and its antiparticle collide and annihilate, could it be more than simple destruction? Could it be a reconciliation of timelines, a meeting of forward and backward travelers at the same point, both erasing and preserving the balance of time itself? This thought lingers, unsettling, mysterious, beyond ordinary human intuition. We are reminded that antimatter is not just a theory. We create it fleetingly in particle accelerators. High-energy collisions produce showers of particles, both matter and antimatter, flashing into existence before vanishing again in annihilation. In those brief moments, we glimpse the mirror world. Positrons streak away, curving in magnetic fields opposite to electrons. Antiprotons leave trails that look familiar but reversed. These are not illusions. They are real, tangible, measurable. In fact, positrons are even created naturally on Earth in thunderstorms, when powerful electric fields split the air and generate bursts of matter-antimatter pairs. Somewhere above us, in the heart of a storm, the mirror flickers into existence. But there is an even stranger detail. Positrons from space bombard our planet constantly, remnants of high-energy cosmic events. They reach Earth silently, colliding with matter and vanishing in sparks of light. We live in a universe where matter's ghostly mirror twin is not just theoretical. It is here, around us, raining down, passing through us, leaving no trace except a burst of energy invisible to the eye. The mirror touches us more often than we realize. The narration shifts to the emotional impact. To live is to take for granted that we exist in a universe of matter. But what if, somewhere beyond our reach, there exists a universe of antimatter? Entire galaxies, stars, and perhaps even beings composed not of protons and electrons, but of antiprotons and positrons. To them, their world would feel normal as ours does to us. They would build, dream, love, and wonder, never knowing that we see them as inverted. And if matter and antimatter worlds ever met, both would vanish in a blaze of light, like two stories colliding into nothingness. The haunting beauty of this thought is inescapable. Our existence may rest on the fragile accident of imbalance. And so, we arrive back at the central paradox. Why did matter survive? Why does our universe prefer one side of the mirror over the other? The The narration allows silence here, letting the question hang in the mind. It is not simply a puzzle of physics, it is a puzzle of existence. Without that imbalance, nothing we know would exist. The mystery of the antimatter mirror is not abstract. It is personal. It is why we are here, to ask the question at all. The section begins to close by tying this back to time. If antimatter truly is matter moving backward in time, then the universe itself may hold within it two intertwined histories, unfolding in opposite directions, each invisible to the other. What feels like annihilation may instead be a crossing of arrows, a merging of timelines. Antimatter becomes not just a physical twin, but a temporal twin, a reflection of ourselves in the river of time, flowing the other way. The final lines of narration sharpen this contrast. We look into the mirror and see our opposite, our twin, our undoing. But the mirror is not passive. It is alive, it is real, and it may be the key to unlocking the greatest mystery of all, whether time itself can flow backward, and whether our story is only half of a larger tale written across two opposing arrows. Antimatter is not just a curiosity of physics. It is the shadow of time itself. In the mid-20th century, as the world stood between the ruins of one global war and the shadows of another, a young physicist, with a mischievous grin and boundless imagination, dared to suggest something so radical that even his peers hesitated. His name was Richard Feynman. To many, he would become a symbol of scientific genius wrapped in playfulness, a man who saw equations as music and physics as a kind of dance. Yet, among his most daring contributions was a simple, audacious idea. Antimatter could be understood as matter moving backward in time. This was not a metaphor, not a philosophical gesture. It was a literal interpretation of the mathematics of quantum electrodynamics. The equations, when studied closely, made no distinction between an electron traveling forward in time and a positron traveling backward in time. Both paths produced the same observable reality. To Feynman, the equations were not just symbols on paper. They were windows into how nature itself behaves. And what they seemed to whisper was that time, which we treat as unidirectional, might, in fact, allow for journeys in reverse, hidden within the mirror dance of particles and antiparticles. The cinematic voiceover paints the scene. A lecture hall in the 1940s, chalk dust in the air, a restless young physicist sketching diagrams that seemed less like equations and more like strange hieroglyphs of the cosmos. Feynman's diagrams, later called Feynman diagrams, reduced the chaos of particle interactions into simple pictures: lines, arrows, intersections. To students, they looked almost childlike. But within them was an entirely new way of seeing the quantum world. In those arrows, Feynman introduced a bold interpretation. An electron traveling backward in time was indistinguishable from a positron moving forward. Suddenly, antimatter was not just a mirror, it was a messenger from another temporal direction. The narration leans into mystery. If time's arrow is so rigid, why would the mathematics so easily allow its reversal? Why would the simplest and most successful description of subatomic interactions contain such ambiguity? Was it a mathematical trick? Or was it revealing something profound about the universe itself? Feynman, playful and pragmatic, often shrugged off the philosophical weight of his own discovery, preferring to see it as a useful tool. But to others, it cracked open the door to unsettling questions. Imagine watching a film reel projected backward. People walk in reverse, shattered glass leaps up and reforms, smoke gathers instead of dispersing. To our intuition, this reversal feels unnatural, even absurd. Yet, at the deepest levels of physics, the equations do not forbid it. They seem almost indifferent to the direction of time. The laws work just as well whether time flows forward or backward. The asymmetry, the feeling that time has a preferred direction, emerges only when we step up to the macroscopic world, where entropy, the second law of thermodynamics, locks us into the forward arrow. But for single particles dancing on the quantum stage, time may not be so stubborn. Feynman's idea did more than reinterpret antimatter. It offered a glimpse of a universe where time was less a river flowing one way and more a stage where actors could move in either direction as long as the script of physics was obeyed. The positron became a clue, a possible signpost pointing to a hidden flexibility of time itself. But this idea also carried unsettling implications. If particles can move backward in time, then could information? Could causality, the very chain of cause and effect that structures our lives, be vulnerable to reversal? The thought is both exhilarating and terrifying. The narration shifts to contrast. On one hand, Feynman's interpretation is elegant, almost poetic, antimatter as matter retracing its steps, the universe holding within it both directions of time like two melodies woven together. On the other hand, it challenges the deepest instincts of human experience. We live as creatures of forward time. We age, we remember the past, but not the future. We act with expectations, not foreknowledge. To suggest that the particles composing us might, in principle, be able to move the other way is to destabilize our entire sense of reality. Yet, physics is not obliged to conform to human instinct. Feynman delighted in this, in showing students that nature is not bound by what feels comfortable. He once remarked that imagination in science is not just about what could be true, but about daring to follow where the equations lead, no matter how strange. In this case, they led him to a world where antimatter might literally be the footprints of matter moving backward. The narration paints a thought experiment. Imagine a single electron traveling through space, weaving between photons, curving in magnetic fields. Now imagine, in the blink of an eye, that electron reverses, retracing its path, not through space, but through time. To us, standing outside, this reversal looks like the appearance of a positron. Emerging, interacting, moving forward. Two interpretations of the same event. One story told in opposite directions. This duality is not just conceptual, it is embedded in how physicists calculate real phenomena, how they predict the outcomes of particle collisions. And yet, as radical as it sounds, the universe seems to conspire to keep this secret hidden. We never observe an electron literally running backward through time. We only ever see the positron behaving as if it were a forward-moving particle with opposite charge. The mirror is always veiled, its truth disguised. This forces us into humility. Physics gives us two equally valid ways to describe reality, but it refuses to tell us which is true. Perhaps both are. Perhaps truth itself is not singular, but layered. A mirror facing another mirror, reflecting endlessly. The narration takes a darker turn. If antimatter is time-reversed, then annihilation, the meeting of matter and antimatter, becomes something far stranger. It is not just destruction, but the merging of two timelines, two opposite journeys meeting at the same point. The light that bursts forth may be more than energy. It may be the release of contradictions, resolving into harmony. Suddenly, what looks like violence becomes reconciliation, a fleeting balance between forward and backward. As the section draws toward its close, the audience is invited to feel the weight of Feynman's wild idea. It is not only a scientific tool, it is a philosophical grenade. It asks us to question whether time's arrow, which seems so absolute, is really as fragile as a human perspective. Feynman himself often laughed at the seriousness others placed upon it, but perhaps that was his genius, to laugh where others trembled, to play where others hesitated. Behind his grin was the courage to take mathematics at its word, no matter how outrageous. And so we leave this chapter with a haunting possibility. Every positron we detect may be a whisper from the other side of time. Every annihilation, a handshake between past and future. Every experiment, a reminder that the universe is not what it seems. Feynman's idea is not just wild. It is a mirror held up to our assumptions, reflecting them backward, daring us to ask whether the flow of time is truly one way, or whether the deepest truth is that all directions are possible, if only we had the vision to see it. Time is the silent stage upon which every story of existence unfolds. We measure our lives by its relentless march, birth to death, cause to effect, beginnings unfolding into endings. Yet, for centuries, philosophers and physicists alike have been haunted by a simple, nagging question. Why does time only flow forward? The equations of physics, from Newton to Einstein, from quantum mechanics to electromagnetism, are astonishingly indifferent to direction. They work just as well if time runs backward. But in our daily experience, there is no mistaking the arrow. Shattered glass does not reassemble, smoke does not leap back into logs. We remember yesterday, but never tomorrow. This tension between symmetrical laws and asymmetrical experience is one of the deepest mysteries of science. The narration slows, building imagery. Picture the universe as a film reel, unspooling, every frame a moment of existence. The frames could be played forward or backward with equal clarity, yet we only experience them in one direction. The question is, what writes the arrow? What pins down time so firmly that, even though the mathematics allows freedom, reality insists on rigidity? For most physicists, the answer comes from the second law of thermodynamics, the law of entropy. It tells us that in any closed system, disorder tends to increase. Heat flows from hot to cold, not the other way. The energy of a system spreads out like ink dispersing in water, never spontaneously condensing back. This creeping of disorder gives time its arrow, painting one side of reality as the future and the other as the past. And yet, there is unease in this explanation. Entropy tells us why systems evolve in a particular way, but not why the universe began in such a low entropy state that there was room for disorder to grow. Why was the cosmos, in its birth cry at the Big Bang, so improbably ordered, so finely structured? Without that unlikely starting point, there would be no arrow of time at all. This is a mystery that entropy alone cannot solve, a riddle buried at the foundations of existence. The narration shifts to contrast. On the one hand, the arrow of time gives us meaning. It is the rhythm that allows stories, memories, history itself, to exist. Without it, existence would be frozen, a static block of events with no sense of before and after. On the other hand, physics whispers that this arrow may not be fundamental. It may be emergent, a large-scale illusion that disappears when we descend into the quantum realm. At the particle level, events do not unfold with such stark directionality. Reactions can move forward or backward in time with equal probability, governed only by the rules of symmetry. If this is true, then the arrow of time may be less a law of nature and more a statistical trick, born from the sheer vastness of the universe and the improbable roll of its initial dice. Imagine, for a moment, a universe where the arrow of time does not hold. A place where memory is not tethered to one direction, where cause and effect blur into a loop, where the future may be as accessible as the past. Such a universe defies our ability to even picture it. And yet, the equations do not rule it out. They leave open the possibility that time, like space, may be traversed in both directions, but that we are creatures locked into one-way perception. If so, then the arrow of time is less a property of the cosmos and more a property of us, of our biology, our cognition, our vantage point within entropy's flow. The narration deepens with imagery. Entropy is like a river, pulling all things toward wider, more chaotic states. We float upon it, our lives carried downstream, powerless to paddle upstream into the order that once was. Yet, perhaps beneath the surface, in the subatomic depths, the river has no preferred direction. There, tiny particles dance with indifference to time's current, sometimes drifting forward, sometimes backward, their movements invisible to us because our entire perspective is already downstream. The arrow of time may be less a universal truth and more a shadow of our position within the flow. But there is an unsettling implication here. If the arrow of time is emergent, not fundamental, then our certainty about cause and effect begins to wobble. What we call causality, the bedrock upon which we build science, law, morality, meaning, may be less absolute than we think. It may be a temporary construct, born of entropy's tyranny, one that could dissolve in the extreme conditions of the cosmos. In black holes, at the singularity of the Big Bang, at the quantum foam where space and time themselves fluctuate, the arrow may not exist at all. In these domains, the idea of before and after could collapse, leaving only timeless interactions, events without sequence, existence without direction. The narration slows to a hushed tone, pulling the audience into awe. The arrow of time, which feels so absolute in our lived experience, may be nothing more than a fragile thread woven into a much larger tapestry. That thread could snap in certain realms, revealing a universe that is timeless, symmetric, indifferent to direction. And yet, within that indifference, we experience the world as irrevocably forward. This paradox is not just scientific but existential. It forces us to question whether the flow of time that defines our lives is an illusion, or whether it is the very essence of what it means to be alive. We end with mystery. Perhaps the arrow of time is not universal but local, a property of our corner of reality. Perhaps other regions of the cosmos, born of different initial conditions, experience time differently, backward, sideways, cyclic. Or perhaps the deepest truth is that all time exists at once, like a block of stone, and our consciousness is merely a chisel moving across it, giving the illusion of flow. The arrow of time is our compass, but the universe may be compassless. What if the only reason time moves forward is because we are built to notice it that way? At the smallest scales of reality, where particles dance in a realm so alien to our everyday senses that it feels like another universe altogether, time does not behave as we expect. The familiar arrow of time, which in our world is so unwavering and absolute, seems to fade, replaced by a strange symmetry. Imagine pressing play on a video of colliding billiard balls. If you ran the footage backward, you would instantly notice the difference. But in the quantum world, replaying the movie often looks exactly the same. The laws governing particles at this level do not care if time flows forward or backward. It is as though nature whispers, time is not fundamental but flexible. This symmetry is not just an abstract mathematical curiosity, it is built into the very equations that describe the universe. Take the Schrödinger equation, the beating heart of quantum mechanics. It predicts how the wave function of a particle evolves, and it is perfectly happy running in reverse. To the equation, the future and the past are simply two directions along a line, interchangeable mirror images. There is no preference, no built-in arrow. And yet we, bound by our senses and the macroscopic world of entropy, only ever experience one direction. This dissonance between the quantum laws and our perception forces a haunting question. Is the arrow of time real, or is it only an illusion stitched together by scale? We can see glimpses of this symmetry in some of the strangest behaviors of particles. Consider antimatter, the mirror twin of ordinary matter. In the 1940s, the brilliant physicist Richard Feynman proposed a daring interpretation. What if antimatter is nothing more than ordinary matter moving backward through time? When a particle and its antiparticle meet, they annihilate, releasing energy. But through another lens, what we are seeing is the collision of timelines, one flowing forward, the other backward, canceling each other out in a flash of light. This interpretation is more than poetic. It emerges naturally from the mathematics of quantum field theory. If true, it would mean that every antiparticle is like a messenger from a reverse temporal dimension, reminding us that time's arrow may not be universal, but relative. And experiments continue to blur the line further. Physicists have observed quantum processes that appear to defy our intuition about temporal order. In certain situations, particles can be entangled across time itself. That is, the behavior of a particle now can be correlated with the state of another particle in the past, as though the influence stretched backward, reaching into history. These are not just wild imaginings but laboratory-tested results, part of the emerging field of temporal entanglement. It suggests that the separation we place between past, present, and future may be thinner than we ever dared believe. Imagine tossing a pebble into a pond. The ripples spread outward in perfect circles, forward in time. But in the quantum world, it is as if those ripples also echo backward, rewriting the surface from which they came. In some interpretations of quantum mechanics, especially the transactional interpretation, waves do not simply propagate forward, but also backward through time, meeting in the middle to create the event we observe. In this view, reality is a handshake across time, a negotiation between past and future that produces the present. This is not just metaphorical, it is one possible explanation for why quantum probabilities collapse into definite outcomes. If true, then the universe is not a one-way street, but a dialogue, a conversation across the timeline. And yet, there is an eerie tension. While the equations allow time reversal, we rarely see it in practice. There are exceptions, though, moments when the symmetry is not perfect. In the 1960s, experiments with subatomic particles called tachyons revealed that nature does, in fact, have a slight bias. Tachyons and their antiparticles should, by the equations, behave in perfect time-reversed symmetry. But they do not. They reveal a subtle asymmetry called CP violation, a tiny crack in the mirror. This discovery was revolutionary because it showed that the universe does favor one direction of time, if only slightly. That small imperfection may even be the reason why matter exists at all. If particles and antiparticles had been produced in perfect symmetry after the Big Bang, they would have annihilated each other completely, leaving only radiation. The fact that we are here suggests the universe has a preference, a tilt toward one side of the temporal axis. But here is where contrast sharpens. On the one hand, CP violation proves that the arrow of time has a microscopic foothold, written into the laws themselves. On the other hand, the overwhelming majority of quantum interactions remain time-symmetric. The cosmos is thus a strange hybrid, mostly reversible at the smallest scales, yet slightly tilted toward irreversibility. This raises profound philosophical questions. Are we the product of that tiny asymmetry, fragile beings born in the cracks of imperfection? Or is the tilt simply a local quirk, one of countless possible realities where time behaves differently? Consider, too, the implications for causality. If particles can interact in ways that disregard temporal order, then our understanding of cause and effect, the foundation of reason and science, may be far less absolute than we think. Imagine an experiment where the measurement you perform today influences the outcome of an event that happened yesterday. This sounds impossible, but quantum mechanics does not entirely forbid it. In fact, the delayed choice experiments, first proposed by physicist John Wheeler, suggest precisely this. The way you choose to observe a particle now can determine how it behaved in the past. To our human minds, this sounds like science fiction, but in the quantum realm, it is an unavoidable consequence of how reality works. The narration leans into wonder and unease. If time symmetry is real at the quantum level, then perhaps the universe is not a flowing river, but a frozen lake, its surface timeless. What we call events may be less like causes and effects, and more like correlations, patterns etched into an eternal block. The arrow of time that we feel may be only the echo of a deeper, timeless reality, one where forward and backward are illusions born of our perception. We are like ants crawling across a painting, mistaking direction for motion, when in truth the entire canvas already exists. And yet, our daily lives are unyieldingly directional. We age, we remember, we act, we choose. To reconcile the quantum reversibility with our irreversible experience is to confront one of the greatest mysteries in physics. It is not enough to say that entropy explains the arrow of time, because entropy itself is statistical, emerging only when we zoom out to vast numbers of particles. Deep down, the universe may not care about arrows at all. It may only care about symmetry. And within that symmetry, small cracks, like CP violation, give rise to everything we know. The section closes in suspense, setting the stage for deeper inquiry. If quantum mechanics allows particles to ignore time's arrow, then perhaps there exist phenomena, particles or even entire realms of physics, that truly move backward in time. The particle that could reverse the flow is not just a theoretical curiosity. It may already be here, hidden in plain sight, waiting for us to recognize it. In the early 20th century, as the foundations of quantum theory and relativity began to reshape our view of the universe, a startling idea emerged, one that would stretch our understanding of time itself. Antimatter, the shadow twin of ordinary matter, carries with it not only opposite charges but perhaps an opposite relationship with time. For every electron, there exists a positron, identical in mass, yet with the opposite electric charge. At first glance, this duality seems simple enough. But when the mathematics of quantum field theory is examined more deeply, something extraordinary reveals itself. Antimatter can be interpreted as matter traveling backward in time. Richard Feynman, always one to play with bold and counterintuitive ideas, illustrated this concept in his revolutionary diagrams that mapped particle interactions. To him, a positron moving forward in time was indistinguishable from an electron moving backward. The math allowed either perspective. In a sense, each time antimatter is created in our universe, a shadow narrative of reverse time emerges alongside it, echoing backward into the past while ordinary matter surges forward. It is as though nature built into its very design a mirror where time does not only run one way. Imagine standing before two mirrors placed opposite each other, the reflections receding into infinity. Each image is a reversal, an alternate direction of gaze. Antimatter, in the same way, becomes a reflection of matter across the temporal mirror. When a particle meets its antiparticle, the collision is not just an explosion of energy. It is, in one interpretation, the reunion of timelines, the meeting point of forward and backward flows. The annihilation flash is not simply destruction but the reconciliation of dual temporal narratives, collapsing into light. This perspective reframes how we might think of time symmetry. For if antimatter truly embodies matter reversed through time, then the universe has always carried within it a fundamental two-way nature. One half of existence stretches into the future, the other retraces into the past. But if that is so, why does our macroscopic world appear so firmly biased toward the forward direction? Why are we not constantly aware of reversed flows playing out around us? The answer may lie in imbalance. While the Big Bang should have created equal amounts of matter and antimatter, something tilted the scales. For reasons we still do not fully understand, matter came to dominate, leaving antimatter rare, fragile, and fleeting. That imbalance itself could be the very reason we experience time in one dominant direction. Antimatter, then, may not just be the twin of matter but the suppressed reminder of a deeper cosmic symmetry that our universe left behind. Its rarity makes it precious, a ghost of the past, a reminder of how things might have been if the mirror had not cracked in favor of matter. Experiments at facilities like CERN attempt to probe this mystery by creating and trapping antimatter. Positrons and antiprotons are generated, bound into exotic atoms like antihydrogen, and studied for differences in behavior compared to their matter counterparts. These experiments are not only about charges and masses, they are quiet interrogations of the universe's temporal balance. If even the slightest deviation is found in how antimatter behaves compared to matter, it could rewrite the story of time's arrow. The mere fact that antimatter annihilates so violently with matter hints at a cosmic incompatibility, as though time itself resists running in two directions within the same space. There are even deeper implications. If antimatter is matter moving backward in time, then, in principle, observing antimatter might allow glimpses into reversed causality. In such a world, what looks to us like an effect could be the cause from the antimatter perspective. A positron drifting in a detector is mathematically an electron returning from the future. In that sense, the future is not unreachable, it is already imprinted into the present, stitched into the antimatter that flickers briefly before annihilation. This interpretation pushes us toward philosophical territory. If antimatter is truly a reflection across the time mirror, then perhaps we should not think of time as linear, but as dual. The universe may be structured not as a single arrow but as two intertwined flows, meeting at every instant, resolving into the now. Our perception, biased by entropy and dominated by matter, only lets us see half of the picture. But the antimatter that occasionally sparks into existence is the evidence that the hidden half persists, invisible, yet essential. The strangeness deepens when one considers black holes. Some physicists speculate that within their singular depths, matter could transform into antimatter, or that time itself might reverse beyond the event horizon. If that is true, then antimatter may not simply be a laboratory curiosity, but a cosmic key, a marker of regions where time folds upon itself. In that view, antimatter is not just a mirror particle, it is a clue to the geometry of space-time itself, hinting that the universe is far stranger and more symmetric than our ordinary senses admit. The narrative here holds its breath between awe and unease. Antimatter is beautiful in its symmetry, yet terrifying in its annihilation. It promises answers to time's greatest riddles, yet resists persistence in a world dominated by matter. Every flash of annihilation is a reminder that two temporal directions cannot coexist without collapse. And yet, hidden in those brief moments is the profound possibility that time is not one-directional, not singular, but a duality, a mirrored structure woven into the universe since the beginning. The section leaves us staring at the mirror, unsettled. If antimatter is indeed the embodiment of time reversed, then our universe is not what it seems. The future may already be written into the present, encoded in the antimatter that whispers back from its annihilation. To pursue the mystery of antimatter is not only to chase after exotic particles but to confront a deeper truth, that we may only be living in one reflection of a larger cosmic whole. Somewhere, in the other reflection, time itself is running the other way. Causality is the bedrock upon which our understanding of the universe rests. The belief that every effect follows from a cause is not just a principle of science, but a rule that guides our daily lives. We expect that if we push a glass, it will fall, not the other way around. But when we enter the quantum world, this certainty begins to blur. Particles flicker in and out of existence, events appear probabilistic, and at the deepest level, the sequence of cause and effect becomes difficult to pin down. The question arises, is causality absolute, or can it crack under the weight of quantum paradoxes? The strange possibility of particles moving backward in time challenges this foundational rule. If an electron, interpreted in one framework, can also be seen as a positron journeying from the future into the past, then what does that say about causality itself? Suddenly, the timeline is no longer linear. What we think of as cause might also be an effect, depending on perspective. Imagine a ripple on a pond, where the wave moves outward and, simultaneously, in reverse, appears to converge back inward. Both interpretations describe the same event, yet from opposing temporal directions. This idea has real consequences. If antimatter can be viewed as matter traveling backward in time, then, in theory, signals or information carried by such particles could defy causality. A message could arrive before it is sent. An outcome could appear before its initiating action. To us, this sounds like science fiction, a world of paradoxes, where the past and future loop endlessly into each other. Yet, in the quiet corridors of theoretical physics, these questions are studied with seriousness, for the math does not outright forbid them. The cracking of causality is not only a theoretical curiosity, it is tied deeply to some of the most profound mysteries in modern physics. Take the EPR paradox and quantum entanglement. Two particles, created together, seem to influence each other instantly, no matter how far apart they travel. To preserve the speed limit of light, one must either abandon locality or accept that something deeper is happening, that events are not simply chained in a linear cause-to-effect order, but are instead woven together in ways that transcend time as we know it. It is not just that one particle causes the other to flip its state. Perhaps both outcomes are tied by a hidden symmetry, existing outside the causal chain altogether. The concept of retrocausality emerges here. The suggestion that the future can influence the past, just as the past influences the future. At first, this seems impossible. How could a choice made tomorrow affect an outcome today? And yet, when experiments in quantum optics hint at delayed choice effects, where decisions made after a photon passes through an apparatus seem to retroactively determine its earlier behavior, the line between before and after wavers. In these moments, the arrow of time is less a rule and more a perception. If causality cracks, the implications ripple outward into every field of thought. For philosophers, it shakes the very foundation of free will. If effects can precede causes, then are our choices truly our own, or are they written into the timeline from both directions at once? For scientists, it raises the question of whether the universe is fundamentally deterministic in a way far stranger than Newton ever imagined. Perhaps all of time exists already, a static block where cause and effect are illusions imposed by our perception of moving through it. The unsettling aspect is not just the possibility of retrocausality, but its consequences for logic. Paradoxes like the grandfather paradox arise. If you could send information back in time, could you prevent the very act of sending it? Physics struggles with such loops, for they suggest contradictions in reality itself. Yet there are frameworks, such as the Novikov self-consistency principle, which suggest that paradoxes resolve themselves. You can act within the past, but only in ways that preserve the timeline. In other words, you can push, but the universe bends to ensure consistency. Still, even this explanation leaves us with a universe stranger than we are comfortable with. A cosmos where the past and future communicate, where causality is not absolute but conditional, demanding that we rethink not only physics but existence itself. For if causality is fragile, then time is not the reliable river we once thought. It is instead a vast ocean, where currents run in multiple directions, sometimes colliding, sometimes converging, always shaping the surface flow we call the present. The imagery of a crack is fitting. Causality does not shatter completely, for the macroscopic world we inhabit still obeys it overwhelmingly. But in the quantum realm, fine fractures appear, tiny fissures where light bends strangely, where particles leap impossibly, where effects sometimes anticipate causes. These cracks may be the key to unifying the deepest laws of physics. They may be the points where relativity and quantum mechanics, currently at odds, finally converge into a single description of reality. The emotions stirred by such cracks are mixed. On one hand, they open the door to wonder, suggesting that time is more flexible, more alive, more astonishing than we ever imagined. On the other, they threaten our sense of stability. If we cannot trust that causes precede effects, then what foundation remains for reason itself? Every scientific experiment, every logical deduction, rests on this assumption. Without it, even truth seems slippery. And yet, perhaps it is in this very slipperiness that truth lies. The universe may not be bound by the linear rules we impose upon it. Instead, it may operate on a deeper harmony, one where causality is not lost but redefined, one where time's flow is less an arrow than a web connecting moments across past and future alike. What we call cracks may actually be windows, showing us glimpses of a reality larger and stranger than causality alone can explain. The thought lingers. If causality can crack, then so can our conception of destiny. Perhaps the future is not only open but already influencing us. Perhaps our present decisions are threads in a larger tapestry, woven from both directions of time. To stare into this possibility is to confront a universe that is not merely vast in space, but vast in time, layered, interwoven, endlessly mysterious. And in those moments when cause and effect blur, we are reminded that what we call reality may be only one interpretation of a deeper, mirrored truth. In the abstract world of mathematics, the universe is stripped down to its barest logic, and there, time reveals its most curious property. Many of the fundamental equations of physics are symmetric under time reversal. This means that if you replace time with its negative, the equations remain unchanged, as if the universe could just as easily run backward as forward, without contradiction. The laws of motion in Newtonian mechanics, the equations of electromagnetism, and even the foundations of quantum mechanics all seem to suggest that the universe itself does not inherently care about the direction of time. The distinction between past and future, so deeply ingrained in our daily perception, appears absent in the language of mathematics. Consider the example of Newton's second law. Force equals mass times acceleration. If a planet orbits a star, the mathematics describes its path perfectly. Now, reverse time. Instead of moving forward in its orbit, the planet moves backward along the exact same trajectory. The equation still holds true. Nothing breaks. The laws do not protest. Similarly, Maxwell's equations, governing the behavior of electric and magnetic fields, remain valid whether time is flowing forward or reversed. In this purely mathematical landscape, time is not an arrow but a coordinate, one that can be flipped without erasing the consistency of the system. Quantum mechanics introduces even more subtlety. Schrödinger's equation, which governs the evolution of quantum systems, is time-symmetric at its core. If you reverse the sign of time, the equation still faithfully describes the evolution of the wave function. This reveals something profound. In the deepest mathematical structure we have to describe nature, there is no preference for forward versus backward. The arrow of time, so strongly felt in our human world, is not dictated by the equations themselves but emerges from other principles, such as entropy and the second law of thermodynamics. It is here that mathematics confronts mystery. If the equations are ambivalent about time's direction, why does the universe seem to insist on a one-way flow? Why do we remember the past but not the future? Why do glasses fall and shatter, but never spontaneously reassemble? Mathematics provides the unsettling answer. The arrow of time is not written into the laws themselves but arises from the initial conditions of the universe. At the beginning of time, the cosmos was in a state of extraordinarily low entropy, a condition of immense order. From that moment onward, disorder has steadily increased, creating the appearance of a forward arrow. But, in principle, nothing prevents a reversal. If the universe had begun in the opposite state, we might experience reality as flowing the other way. The concept of CPT symmetry sharpens this picture even more. In physics, CPT stands for charge, parity, and time. It is a theorem that states, if you flip the charges of all particles, mirror their spatial coordinates, and reverse time, the laws of physics remain exactly the same. This is one of the most fundamental symmetries known, embedded in the very foundations of quantum field theory. It implies that a universe moving backward in time, with reversed charges and mirrored spatial orientations, would be indistinguishable from our own. In other words, there could be a reflection of our cosmos where time flows in the opposite direction, and yet all the rules remain intact. For a moment, imagine this parallel world. In it, what we call the future is their past, and what we call the past is their future. Their suns burn backward, their civilizations collapse before they rise, and their people grow younger as their memories dissolve into unborn moments. To us, such a vision seems alien and nonsensical, but mathematically, it is as valid as our own experience of time. If equations allow it, who are we to dismiss it? This symmetry has inspired some of the boldest theories in physics. Some researchers suggest that, at the moment of the Big Bang, two universes were born, expanding in opposite temporal directions. One flows into what we call the future, the other into what we would see as the past. From the perspective of each universe, time flows normally, forward. But from the outside, one is the mirror image of the other. If this is true, then our cosmos is not alone but paired with its temporal twin, born from the same origin but destined to move in reverse. Mathematics also exposes the few rare cracks in this symmetry. Certain interactions in particle physics, specifically involving the weak nuclear force, do not remain the same under time reversal alone. They exhibit what is called CP violation, a tiny preference that breaks the perfect balance. This violation is critical, for without it, matter and antimatter would have annihilated each other completely in the early universe, leaving behind nothing but radiation. The asymmetry allowed matter to dominate, and thus allowed stars, planets, and life to exist. Here, mathematics whispers a deeper truth. Time reversal symmetry is nearly perfect but not absolute. It is in the exceptions that the universe gains its character, its substance, and its story. Still, the broader symmetry remains. Most of the laws we know treat past and future as equal. The irreversibility we see arises from statistical tendencies, not absolute prohibition. The shattering of glass is more likely than its reconstruction, not because the laws forbid the reverse, but because the probability is so astronomically small that it may as well be impossible. Mathematics allows it, reality resists it. In this gap between theory and perception, mystery grows. The mathematics of time reversal leaves us with a paradoxical sense of awe. On the one hand, it reduces the arrow of time, so fundamental to human existence, to a mere illusion of initial conditions. On the other, it elevates the laws of physics into something almost eternal, impartial, and transcendent, unbound by the constraints that govern us. The future and the past, it tells us, are not opposites but reflections of one another, held in balance by equations that do not care which way we walk through them. Yet mathematics is not just abstract. It hints at possibilities. If time can be reversed in equations, could it one day be reversed in reality? Could technologies exploit this symmetry, manipulating particles to move against the current of causality? Could we send signals into the past, alter events, or glimpse futures not yet unfolded? These questions straddle the line between science and speculation, but they arise inevitably from the symmetry at the heart of physics. To stare into these equations is to feel the fragility of our everyday sense of time, and to glimpse a reality where past and future dissolve into a single, timeless order. In the vast zoo of subatomic particles, few are as elusive as the neutrino. They are called ghost particles for a reason. Trillions of them pass through your body every second, born from the nuclear furnaces of stars, from radioactive decay in the Earth, and from violent cosmic events far across the universe. They are nearly massless, almost impossible to detect, and barely interact with matter at all. For decades, neutrinos were considered little more than a curiosity, tiny players in the cosmic drama, whispering between atoms but never leaving much of a trace. Yet, in recent years, neutrinos have stepped into the spotlight as candidates for revealing the deepest mysteries of time itself. Some experiments suggest that these ghostly particles may not only move through space in ways we barely understand, but may also hold the key to whether time can truly run backward. The story begins with the discovery of neutrino oscillations, a phenomenon that shocked the physics community. Neutrinos come in three flavors: electron neutrinos, muon neutrinos, and tau neutrinos. But unlike most particles, neutrinos do not remain fixed in a single identity. As they travel, they shift, morphing from one flavor to another in a quantum dance across cosmic distances. This shape-shifting ability implied something radical. Neutrinos must have mass, however small. The standard model of particle physics, the reigning framework for understanding the subatomic world, had assumed they were massless. The discovery forced a revision of fundamental theory, and with it came a question. If neutrinos already defy expectations, what else might they reveal? Attention soon turned to the possibility of CP violation in neutrinos. Cp stands for charge and parity, the symmetry that treats particles and their mirror image antiparticles as equal. If Cp symmetry held perfectly, the universe should contain equal amounts of matter and antimatter. But it doesn't. The observable universe is overwhelmingly made of matter. Somewhere in the early cosmos, the balance was broken, tipping reality toward matter and allowing stars, galaxies, and life itself to exist. Understanding this asymmetry is one of the great unsolved puzzles of physics. And neutrinos may hold the answer. Experiments such as T2K in Japan and NOVA in the United States have been firing intense beams of neutrinos across hundreds of kilometers to study their oscillations. By comparing how neutrinos and antineutrinos change flavors during their journey, scientists are searching for differences, a sign of Cp violation. Early results have hinted that neutrinos may indeed behave differently from their antimatter counterparts. If confirmed, this would be one of the most profound discoveries in modern science, evidence that the universe itself contains an inbuilt preference, a tiny asymmetry that gave rise to everything we know. But beneath this quest lies an even stranger possibility. Some interpretations suggest that the odd behavior of neutrinos could be linked to time reversal. In particle physics, Cp violation is intimately connected to T violation, the breaking of time reversal symmetry. If neutrinos show a difference in how they oscillate compared to antineutrinos, it may imply that time itself is not symmetric at the most fundamental level. Imagine a neutrino moving forward in time, oscillating from one flavor to another. Now reverse the movie, run time backward, and the equations should describe the oscillation in reverse. If the results are not identical, if nature shows a preference for one direction over the other, then time reversal symmetry has been violated. For neutrinos to reveal this would mean that these ghostly particles are not only messengers from the stars, but also carriers of information about the one-way flow of time. This is where the puzzle deepens. Some theorists have suggested that neutrinos may actually move backward in time under certain conditions, or that their behavior can only be fully understood if we allow for the possibility of time-reverse states. In this picture, the neutrino we detect might not be a simple forward-moving particle, but part of a larger quantum system that includes motion into the past. It sounds fantastical, almost science fiction, but mathematics leaves the door open. And experimental hints, though faint, keep drawing physicists toward the mystery. Consider the sterile neutrino, a hypothetical fourth kind of neutrino beyond the three known flavors. Some experiments, such as the LSND and Minibuini projects, have observed anomalies that do not fit neatly into the three-flavor oscillation model. The data hint at the possibility of sterile neutrinos, which would interact even less with matter than their already elusive cousins. If sterile neutrinos exist, they could be linked to time symmetry breaking and even to the dark matter that fills the cosmos. Detecting them would require rethinking not only the standard model, but also our understanding of time and causality itself. The neutrino puzzle gains another layer when we consider the idea that neutrinos might be their own antiparticles. Such particles are called Majorana particles, after the Italian physicist Ettore Majorana, who disappeared mysteriously in 1938. If neutrinos are Majorana particles, then a neutrino and an antineutrino would be indistinguishable, merely two faces of the same entity. This strange property could explain why the universe has more matter than antimatter and could again connect neutrinos to the arrow of time. In some formulations, the existence of Majorana neutrinos implies a natural mechanism for time asymmetry, embedding the direction of time into the very identity of these ghostly travelers. Around the world, enormous experiments are underway to probe these questions. Deep underground laboratories, shielded from cosmic rays, are building vast detectors filled with liquid argon or heavy water, waiting for the faint signals of neutrino interactions. The Dune experiment in the United States aims to send a beam of neutrinos from Illinois to South Dakota, over 1,300 kilometers away, to measure oscillations with unprecedented precision. Hyperchemiocandi in Japan, a massive water tank buried beneath a mountain, will study neutrino behavior with unparalleled sensitivity. These projects are more than feats of engineering. They are attempts to listen to the whispers of the universe, to detect the subtle fingerprints of time written in the behavior of particles that barely exist. The stakes are enormous. If neutrinos truly break CP symmetry in a measurable way, they could explain why the universe exists in its present form. If they hint at deeper time reversal violations, they could challenge our most fundamental assumptions about the symmetry of nature. And if sterile or Majorana neutrinos are discovered, they could provide direct evidence of phenomena beyond the Standard Model, pulling us into a new era of physics. In each case, the neutrino is no longer just a ghost particle. It is a messenger from the foundations of reality, carrying secrets that could redefine our understanding of time itself. Yet, as with so many mysteries, the answers remain just beyond reach. The data are tantalizing, but not conclusive. Some experiments suggest asymmetry, others remain inconclusive, and still others contradict one another. The ghostly nature of neutrinos makes them slippery targets, as though time itself were playing a game of hide and seek with us through these particles. Each detection is rare, each event uncertain, and the possibility of false signals always looms. Still, the pursuit continues, driven by the belief that somewhere in the dance of these elusive particles lies the key to one of the greatest riddles of existence. The neutrino puzzle is more than an experimental challenge. It is a philosophical provocation. If the smallest and most elusive of particles can carry the imprint of time's arrow, then time itself is not a universal flow, but a property rooted in the quantum fabric of reality. If neutrinos whisper of a universe where time can tilt, skew, or even reverse, then perhaps our daily sense of inevitability is just a shadow cast by deeper laws we do not yet fully understand. The neutrino forces us to confront the possibility that the arrow of time is not as rigid as it seems, that causality itself may bend, and that the future and past may not be as strictly separated as our experience insists. In this sense, the neutrino puzzle is not only scientific, but existential. It reminds us that we are creatures bound by perception, peering through narrow windows at a universe whose full story may be stranger than imagination allows. Somewhere in the silence of the cosmos, ghost particles stream endlessly, carrying with them the possibility of answers. Whether they are moving forward in time, backward, or both at once, they beckon us toward a deeper understanding of what time truly is. When Albert Einstein introduced the theory of relativity in the early 20th century, he did more than revolutionize physics. He redefined time itself. Before Einstein, time was thought to be absolute, a universal clock ticking the same for everyone, everywhere. Newton's vision had held sway for centuries. Space was a stage, and time was the rhythm upon which the universe danced. But relativity shattered this simplicity. It revealed that time is not absolute, not universal, but relative, woven together with space into a single fabric that bends and stretches under the weight of matter and energy. The flow of time, Einstein showed, is not the same for all observers, and this insight remains one of the most counterintuitive and transformative discoveries in human thought. At the heart of relativity is the notion that the speed of light is constant. No matter how fast you move, if you measure the speed of light, it always comes out the same. This single principle led to startling consequences. For one, time is not a rigid backdrop. Instead, it depends on your motion. If you are moving quickly relative to someone else, your clock ticks differently from theirs. This is called time dilation. To someone standing still, a moving clock runs slower. To the person carrying that moving clock, nothing seems unusual because their own passage of time feels normal. But when two observers compare notes, they find disagreement. The faster you travel, the more slowly your time appears to flow. This is not just theory, it has been confirmed countless times. Atomic clocks carried aboard high-speed jets or satellites show measurable differences from identical clocks left on the ground. The Global Positioning System, GPS, depends on correcting for these relativistic time effects. Without such corrections, our maps and navigation tools would quickly drift into uselessness. Relativity is not only a philosophical upheaval, it is a practical fact of modern technology. But beneath the mathematics lies something deeper. Relativity makes time personal. There is no single, universal now. Each observer carries their own slice of reality, their own flow of moments, stitched into the fabric of space-time. Einstein's general theory of relativity deepened this vision. If special relativity tied time to motion, general relativity tied it to gravity. Massive objects bend space-time, and this curvature dictates how time flows. Near a heavy mass, such as a planet or a star, time runs more slowly than in empty space. This is not merely a metaphor. It has been measured on Earth, where clocks at sea level, closer to the planet's center of gravity, tick more slowly than clocks placed on mountaintops. In the vast cosmos, the effect becomes even more dramatic. Near a black hole, where gravity warps space-time to an extreme, time slows almost to a standstill. To an outside observer, someone approaching the event horizon appears frozen, their moments stretched infinitely thin. To the person falling, time seems normal, but the universe around them races forward. Here, relativity reveals its most unsettling implication. Time is not universal, but elastic, dependent on position and motion, warped by the structure of reality itself. This insight forces us to reconsider the arrow of time. We usually think of time as flowing uniformly, carrying all of us in the same direction from past to future. But relativity shows that this flow is neither universal nor absolute. Instead, time is more like a river with many currents. Each observer drifts along their own stream, and while the streams all flow forward, their rates differ, their rhythms diverge. For some, time may pass quickly. For others, slowly, depending on their journey through space-time. The arrow still points in one direction, but relativity fractures the uniformity, creating a mosaic of temporal experiences. Relativity also challenges our idea of simultaneity. In Newton's world, events happened either at the same time or not. There was a universal clock to compare everything against. But relativity shows that simultaneity depends on the observer. Two events that appear simultaneous to one person may not be simultaneous to another moving at a different velocity. This means that even the sequence of now is subjective. The present is not universal, but relative to perspective. The past, present, and future are not cleanly divided slices of the cosmos. Instead, they form a continuum, stitched differently depending on where you stand and how you move. This realization has led some physicists and philosophers to adopt the block universe interpretation. In this view, space-time is a four-dimensional whole containing all past, present, and future events. The flow of time, in this interpretation, is not fundamental, but emergent, a product of consciousness moving through the block. The universe is not being written as we go. It is already written, every moment etched into space-time. We do not create the future, we inhabit it. Relativity lends weight to this unsettling picture, where time is less a river than a landscape. All of time exists, and what we call the present is simply the place we occupy in that landscape. Yet even if relativity suggests a block universe, our experience of time as a flow is undeniable. We live inside a sequence, carried along by a sense of before and after, of cause and effect, of growth and decay. This tension between physics and experience is part of the enduring mystery of time. Relativity dismantles the idea of absolute flow, but it cannot erase the arrow we feel. Instead, it reframes it. The arrow is local, personal, dependent on perspective, but nonetheless real in our lived existence. One of the most famous demonstrations of relativity's impact on time is the so-called twin paradox. Imagine two twins. One remains on Earth, while the other travels on a spaceship at near light speed and then returns. When they reunite, the traveling twin is younger. Time has flowed differently for each. This is not a trick of perception, but a physical reality confirmed by experiment. The paradox lies only in our intuition, which expects time to be absolute. Relativity shows that time is not democratic. It does not treat all observers equally. Motion and gravity shape the rhythm of existence, leaving some younger, some older, even if they began at the same point. This relativity of time has profound implications for cosmology. When we look at distant galaxies, we are not seeing them as they are now, but as they were millions or billions of years ago. Light takes time to travel, and relativity assures us that there is no single now that encompasses both our vantage point and theirs. Each galaxy, each star, each observer carries its own clock, its own now. The universe is not synchronized, but alive with a chorus of shifting tempos. To ask what the universe is doing now is to ask a meaningless question, because now is not universal. It is fractured, relative, woven into space-time itself. Relativity also opens the door to speculation about time travel. If time is elastic, if it can stretch and warp, might it also loop back on itself? The equations of general relativity permit solutions where closed time-like curves exist, paths through space-time that return to their starting point in time as well as space. In theory, such curves could allow travel to the past. Rotating black holes, wormholes, and other exotic geometries have been proposed as gateways. Whether these exist in reality is another matter, but the mathematics does not forbid them. Relativity then hints that time's rigidity may be an illusion, that under extreme conditions even causality might bend. Still, relativity does not erase the arrow. The second law of thermodynamics, with its insistence on increasing entropy, remains untouched. While relativity reframes time as relative and personal, thermodynamics insists on its direction. Together, these two perspectives create a paradoxical vision. Time is flexible in flow but rigid in direction. It can be stretched, slowed, or accelerated, but it cannot be reversed. In the marriage of relativity and thermodynamics, we glimpse both freedom and constraint, a universe where time is malleable, yet inexorably one way. The flow of time in relativity is, in the end, a story of humility. It reminds us that our intuitions, shaped by daily experience, are poor guides to the deeper truths of reality. Time is not a single uniform current, but a collection of rivers, each winding through space-time in its own rhythm. We are travelers in one such current, perceiving its flow as natural, even inevitable. But relativity shows us that others drift differently, that the universe is filled with many tempos of time. The arrow still points forward, but the path is not the same for all. To grasp this is to glimpse the strange and wondrous reality that lies beyond common sense, where time is no longer a background, but a participant in the drama of existence. The arrow of time is one of the most profound mysteries in science and philosophy. Every day, we live within its grasp, experiencing the relentless forward motion from past to present to future. We cannot rewind our lives, cannot unspill a glass of water, cannot turn smoke back into firewood. Yet the laws of physics, as written in their equations, show no preferred direction. Whether time runs forward or backward, the mathematics still holds. This mismatch between our lived experience and the symmetry of physical laws demands an explanation. At the heart of that explanation lies entropy. Entropy is a measure of disorder, of how energy and matter are distributed. When systems evolve naturally, they tend to move from order to disorder, from low entropy to high entropy. A deck of cards, carefully sorted by suit and number, is ordered, low in entropy. Shuffle the deck, and disorder increases, entropy rises. Pour cream into coffee, and the swirls mix until a uniform color remains. Energy spreads out, states become less organized, and entropy grows. This principle is enshrined in the second law of thermodynamics, one of the most fundamental laws in science. In a closed system, entropy never decreases. It is this law that gives time its arrow. The direction we call the future is simply the direction in which entropy increases. The past is the low entropy state behind us, the future, the higher entropy state ahead. Everything else in physics may be reversible, but entropy is not. Once disorder spreads, it does not naturally contract. The broken glass does not reassemble. The cooled ashes of a fire do not leap back into flame. This asymmetry gives time its relentless flow, its one-way street. But why does entropy increase at all? To understand, one must consider probabilities. There are far more ways for matter and energy to be disordered than to be ordered. A neat arrangement is fragile, rare, and easily lost. A messy arrangement is robust, common, and overwhelmingly more likely. Imagine tossing a handful of sand onto a smooth floor. For the grains to all land in a perfect circle is not impossible, but it is vanishingly improbable. Almost every toss leads to random scattering, to disorder. In this way, the forward march of entropy is not enforced by some hidden force, but emerges from statistics. The universe moves toward the probable, and disorder is more probable than order. This statistical view clarifies why the arrow of time is so strong in daily life. In practice, entropy increases with near certainty because the number of disordered states so vastly outweighs the number of ordered ones. This overwhelming imbalance creates the illusion of an irresistible law when, in truth, it is probability at work on a cosmic scale. The second law is not inviolable. In principle, tiny fluctuations can produce local decreases in entropy, and indeed, such fluctuations occur. But on human scales, they are negligible, drowned out by the tide of increasing disorder. The role of entropy in defining time's arrow has profound consequences for our understanding of the universe. If the second law dictates the flow of time, then the ultimate fate of the cosmos is entwined with entropy's inexorable rise. The early universe, born in the Big Bang, was in a state of extraordinarily low entropy. Matter was uniform, energy condensed, potential for order high. As the universe expanded, structures emerged: stars, galaxies, planets, life. All of this blossoming complexity has been fueled by the gradual increase of entropy, by the release of stored order into ever wider disorder. The universe's history is the story of entropy unfolding. Looking ahead, the arrow of time suggests a bleak destiny. As entropy increases, usable energy diminishes. Stars will burn out, galaxies will fade, and matter will spread thin across an ever-expanding void. This scenario, known as the heat death of the universe, envisions a cosmos where entropy has reached its maximum. With energy evenly distributed, no further work can be done, no further structures formed. Time, in a sense, will lose its meaning because nothing new will happen. The arrow will stretch toward a future without change, a frozen eternity. Yet entropy is not simply destruction. It also creates. The same principle that drives disorder is what allows order to exist locally. Life itself thrives in defiance of entropy, maintaining order within cells, within bodies, within ecosystems. But this order is temporary, carved out by exporting disorder elsewhere. The Earth, bathed in energy from the sun, uses that energy to sustain life. But in doing so, it radiates heat into space, increasing overall entropy. Order in one place is paid for by disorder in another. Thus, entropy is not an enemy of complexity, but its partner, shaping the conditions under which structures arise and persist. This paradoxical relationship between order and entropy is seen across nature. A star forms when a cloud of gas collapses under gravity, creating a hot, bright sphere. The process increases entropy overall, even as it produces the ordered structure of the star. A hurricane emerges as a swirling vortex of wind and water, apparently ordered, yet driven by the flow of energy from warm ocean to cool sky. Order arises not in spite of entropy, but because entropy is increasing. Local order blooms in the service of global disorder. The arrow of time, then, is not merely a line from simplicity to chaos, but a dynamic interplay where order and complexity can flourish, even temporarily, within the larger march toward disorder. It is in this window, this fragile gap between low-entropy past and high-entropy future, that life and consciousness exist. We are children of the arrow, born in the brief moment when the universe allows complexity, destined to vanish as entropy eventually smooths all patterns away. Philosophers have long wrestled with the implications of entropy for free will and meaning. If the arrow of time is determined by statistics, if the universe is sliding irreversibly toward disorder, does this strip our choices of significance? Some argue the opposite. That meaning derives precisely from impermanence, from the fragility of ordered structures against entropy's tide. A flower is beautiful not despite its decay, but because of it. Our lives are precious because they are fleeting. Entropy ensures endings, but in doing so, it gives weight to beginnings. A deeper puzzle lies in the beginning itself. If entropy always increases, why did the universe start in such a low entropy state? This question remains unanswered. The Big Bang's initial conditions appear improbably ordered, and yet, without them, the arrow of time would not exist as we know it. Some physicists speculate that the laws of physics themselves enforce such beginnings, while others propose that our universe is one of many, each with different entropy histories. Still others suggest that time itself may be cyclical, with entropy resetting in ways we cannot yet comprehend. Whatever the answer, The mystery of the low-entropy origin remains one of the greatest unsolved questions in science. In daily life, entropy is both an abstract principle and an intimate companion. We feel it in the aging of our bodies, in the decay of memory, in the crumbling of buildings, and the erosion of mountains. We see it in every act of consumption, every transformation of energy. Entropy is not only a scientific law, but a lived experience, the backdrop of existence. It defines the arrow that carries us forward, shaping our perception of past, present, and future. The arrow of time, created by entropy, also underpins storytelling, culture, and history. Human narratives depend on sequence, on change, on cause leading to effect. Without entropy, there would be no stories, no progression, no anticipation of what comes next. Time's arrow gives life its drama, and entropy is the invisible force that drives the plot forward. It is in this sense that science and human meaning converge. Both are shaped by the irreversible march from low entropy to high. In the end, entropy is both the destroyer and the creator. It erases patterns but allows patterns to form. It smooths the universe but gives rise to its richness along the way. The arrow of time is its gift and its curse, a reminder that we live in a cosmos where disorder is destiny, but where fleeting order is possible, precious, and profound. To contemplate entropy is to face the impermanence of all things, yet also to marvel that anything exists at all within its relentless tide. In its paradox lies the essence of our temporal existence, fragile order sustained in the midst of inevitable disorder, a brief moment of beauty in a universe rushing toward equilibrium. The story of the universe is inseparable from the story of time, and the story of time is ultimately inseparable from entropy. If entropy defines the arrow that points toward the future, then the destiny of the cosmos must be traced along that arrow to its ultimate conclusion. The second law of thermodynamics tells us that energy spreads, order declines, and disorder grows. As this process continues across unfathomable spans of time, the universe drifts toward a final state known as heat death. It is not an explosion, not a collapse, not a violent end, but a fading, a thinning, a slow and inevitable unraveling of change itself. The heat death of the universe represents the point at which entropy reaches its maximum, when energy is so evenly distributed that no further work can be done, no new patterns can emerge, no fires can burn, no stars can shine. It is the end of history, the cessation of becoming, the silencing of the cosmic symphony. To understand this concept, one must consider what makes activity, life, and structure possible in the first place. Stars shine because they are gradients of energy, hot at their cores and cooler at their edges, releasing light and heat into surrounding space. Planets orbit stars and sustain climates because they are embedded in flows of energy from one state to another. Life itself is powered by these gradients, drawing order from disequilibrium, harnessing flows of energy from high to low, from sunlight to biomass, from chemical reactions to thought. But when the universe reaches thermal equilibrium, when every particle shares the same average energy, when all gradients have vanished, there will be no difference to exploit, no imbalance to drive change. With no contrasts, there can be no processes. Without processes, time as we know it will lose meaning. This future is unimaginably distant. The stars that currently dot the night sky are young compared to what is to come. For trillions of years, stars will continue to form, shine, and die, but eventually even this cycle will end. The hydrogen fuel that feeds stellar furnaces will be exhausted. New stars will no longer be born. The existing stars will burn out one by one, collapsing into remnants, white dwarfs, neutron stars, black holes. The cosmos will grow darker as the light of stars fades, galaxies dimming into obscurity. The night sky will no longer sparkle with constellations but sink into a quiet emptiness, punctuated by cold remnants. Yet even in this long twilight, processes will continue. White dwarfs will cool into black dwarfs, cold, invisible cinders adrift in the dark. Neutron stars will slowly radiate their stored heat into space until they too fade. Black holes will dominate, swallowing matter and merging in rare collisions. But even black holes are not eternal. According to Stephen Hawking's theory, they emit radiation, losing energy over vast timescales. This radiation, though weak, ensures that black holes eventually evaporate. It may take 10 to the power of 100 years or more, but in the end, even the darkest giants will vanish, leaving behind only a thin mist of low-energy photons, electrons, and neutrinos drifting in ever-expanding space. As the universe stretches, this radiation itself will cool. Wavelengths will elongate, temperatures will approach absolute zero. Energy will become evenly distributed across a cosmos grown vast beyond comprehension. The potential for change will disappear, for there will be no unevenness to exploit, no gradient to harness, no imbalance to drive events forward. In this state of maximum entropy, the universe will have reached heat death. The very term heat death is paradoxical, for it does not describe fiery destruction but eternal stillness. It is the cessation of difference. In a sense, it is not death but eternal sameness. Time as we perceive it depends on change, on the difference between what was and what is, on the transformation of energy from one state to another. When no transformation is possible, when the universe has achieved a perfect monotony of energy, the flow of time itself will become irrelevant. The future will be indistinguishable from the present indistinguishable from the past. This prospect is staggering, not only in its scale but in its philosophical weight. If the universe has an ultimate end in heat death, what does this mean for meaning itself? Human civilizations rise and fall within the blink of cosmic time, yet our minds can contemplate the far future with startling clarity. To imagine heat death is to face the impermanence of all things, not only of individuals and species but of stars, galaxies, and the very conditions for existence. In such a vision, nothing escapes entropy. Nothing endures. Some thinkers see this as a profoundly nihilistic conclusion. If everything ends in stillness, if time itself ceases to matter, then all our striving, our art, our knowledge, our achievements are destined to vanish without trace. The universe is indifferent, and its destiny is silence. Others, however, draw a different lesson. If everything must end, then the fleeting is precious. If all order is temporary, then the very fact that it exists at all is extraordinary. The cosmos, in this view, is not diminished by its ending but made wondrous by its brief flowering of complexity in the face of inevitability. There is also the question of whether heat death is truly final. Physics is not yet complete, and the ultimate nature of the cosmos remains uncertain. Some theories suggest that the expansion of the universe might reverse, leading to a big crunch, though current evidence favors continued expansion. Other theories propose the possibility of quantum fluctuations even in a high-entropy universe, random fluctuations that might spawn new regions of order. In this scenario, heat death might not be an end but a seedbed for new beginnings. A rare fluctuation could create a pocket of low entropy, igniting a new Big Bang, birthing a new universe. In this way, the heat death of one cosmos could be the womb of another, an eternal cycle of birth and death stretching beyond imagination. Still, even such speculative possibilities remind us of the limits of knowledge. For now, the best supported model suggests that our universe is headed toward heat death. Whether that death is absolute or a transition to something new remains unknown. The mystery of time's ultimate fate persists, reminding us that the era we follow today is both certain and uncertain, certain in its direction toward entropy, uncertain in its ultimate destination. For human beings, contemplating heat death is both humbling and liberating. It dwarfs our lives, reminding us that we exist for the briefest of instants in a universe whose story spans quadrillions of years. Yet it also highlights the uniqueness of our moment. We live in a universe still ablaze with stars, still rich with gradients of energy, still capable of supporting life, thought, and culture. We inhabit a cosmic springtime, a temporary interval between the low-entropy beginnings and the high-entropy end. To know that this time is fleeting gives it value. To know that everything will one day vanish lends urgency to cherish what exists now. The heat death of the universe is not only a scientific prediction but a philosophical mirror. It reflects back to us questions about meaning, permanence, and the nature of time. It forces us to confront the paradox of existence, that something so vast and magnificent is ultimately impermanent, that time itself, the very medium of our lives, may have an end. In contemplating the silence of the far future, we are reminded of the fragile music of the present. Perhaps then the lesson of heat death is not despair but wonder. The universe, by the laws of physics, need not have produced stars, galaxies, planets, or life. It need not have created beings capable of understanding entropy, of envisioning its end. Yet it did. For a brief time, the cosmos is alive with patterns, beauty, and thought. That these will vanish does not negate their existence. On the contrary, it makes them all the more extraordinary. The end of time, far in the future, should not paralyze us with dread but inspire us to embrace the fleeting miracle of the present.